And my intros for all the speakers will be somewhat brief. Their bios are on the website, and I want to give the time to them to present the material and for Q&A. So first with us is Charles Eckel of Cisco Systems. Charles is a developer advocate and has been in the industry about 20 years in different roles. And for more information, you can see his biography on the website. So without further ado, Charles, take it away.
Great. Thank you very much for that great intro, Chris. And yeah, happy to be here. As Chris mentioned, Charles Eckel. And in my role as a developer advocate, I get to work with a lot of developers. I'm very passionate about open source and also internet standards. And so the talk I want to give today is on applying those to the field of network programmability, something which can be a bit daunting to many engineers who kind of want to overcome that hurdle of getting started with programming, and hopefully show you how open source and standards make network programmability something you can tackle and actually quite easy. So interesting study here. One of the things that came out of it was that human error is the #1 cause of network outage. And that's human error in multiple different forms. I don't think this really comes as a surprise to many people. Making mistakes is, to err is human. Just because, as human beings, when we do a task repetitively, sure, we perhaps get better at it, but we don't get perfect at it, and we certainly don't necessarily enjoy the repetition either. It becomes quite tedious. And we know that computers are actually much more predictable. They're great at doing tasks over and over again and getting it exactly right. So there's certainly room for improvement here in this area. Now, so as easy as flipping a switch. That's what I'd like to, hopefully, at the end of this talk, end of this 30 minutes, you agree with me that on my belief that network programmability and using network APIs can be as easy as flipping a switch. Electricity is a pretty complicated topic. How many of you are electrical engineers, or at least taken some electrical engineering classes? Yeah, there's a lot going on in the study of electricity and learning how to, all the peculiarities of it. But we all know how to do this. We all know how to flip a light switch and be masters of electricity, right? So very much the same, I think, with the APIs that are provided by the network today. As a network engineer, picking up the development skills that you need to automate your network is just as easy, hopefully as easy as flipping a switch. So just going to start from the ground up. First of all, what is an API? I've already mentioned it a few times. Application programming interface. Really just a way for two applications to talk to each other. And what APIs let you do is extend the functionality of something, or to interact with it, or to automate a task. You can build applications using APIs. You can extend the feature set of a product using APIs. We've all worked with many different APIs. One of the APIs is typing a URL into a browser and having it give you a web page back. When you do that, you're actually interacting with an API. And of course, the subject of the talk, you can use APIs to program networks too. So I want to focus on a particular class of API or type of API called a REST API. REST stands for Representational State Transfer. It's an API style, and really what it means is that a given API adheres to the principles of a REST API. I'm not going to go into the details of what those are, but it's basically some pretty well-specified principles around a client-server exchange where there's some very well-defined state that exists on a server, and then the client has well-defined APIs or mechanisms through which to interact with that state. It scales very well due to the nature of the way it's defined. One of the really nice principles is the server doesn't need to keep any state about the clients that are connecting to it. So that gives you some really nice scalability. And that's why you've seen web applications and web services scale so nicely and take off as much as they have. The basic flow of a REST API, and sorry, this may be a little hard to read, but basically when the user of the API, the client, will send a request. In this case, it's an HTTP GET request to a server, which in this case is represented by Debbie, our friendly bot over there. Now, when Debbie gets this, does some processing on it, and that processing is not part of the contract. The client, the person over here on the left, doesn't need to worry about what that is. But at some point, a response will come back, and that is well-defined. Given a certain request, what should that response be? What is the format of that response? In this case, it's a 200 OK coming back with the information that was requested. And looking at the screen, it looks like the user was requesting a web page in this case. So let's look at a REST request in a little bit more detail. The way you build up a REST request and specify which resource you're looking for is by constructing what's known as the URI. And what I'm showing here are the components that always exist with a URI. First of all, the protocol. REST APIs can use different protocols, but typically different transport protocols, but typically they use HTTP, HTTPS, and that's what I'll be focusing on in this talk. The second part is the server or host that is hosting the API, right? The API server. In this case, I'm going to use something that we're hopefully all familiar with, a deck of cards. And there's this API hosted at deckofcardsapi.com. And this is a publicly available server if you want to try this out yourself. The resource I'm going to request in this case, I want to interact with the API and I want to ask for a deck, and specifically a new deck of cards. So the request URI is built up with those components that specify the request I'm trying to make. Now, the other important part, in addition to the request URI, is the HTTP verb. And these HTTP verbs map to what's known as the CRUD operations, to create, read, update, and delete a resource. And they're mapped to the HTTP verbs, post, get, put, patch, and delete, as you see there. Post to create something new, get to read something, put and patch to update something, and then delete to delete something. The other important thing to know is the status code. In our example, we made a GET request and we got back a 200. 200 class responses are typically successful responses, meaning that your request was understood and there's some information that will be coming back to you. 400 class responses generally mean there's something wrong with your request. Perhaps it's malformed. Perhaps you needed to provide credentials and you didn't. And then a 500 class typically means the server had an issue with your request. So there may not, unfortunately, be anything you can do. There's a problem on the server side. So you always have to look at the response code coming back, because that indicates if you're going to be getting back the information you requested or if maybe there's an issue. Okay, fortunately, there are some really nice tools for working with REST-based APIs, and I want to talk about a few of those here. One, as I mentioned earlier, just making a request in your browser. You're actually interacting with the REST API right there. Postman, how many of you have heard of Postman or ever used Postman? It's a great tool for building up sets of REST requests and storing them and then using them. And then I'm going to also, because it's about network programmability, I'm also going to look at Python, which is a language, a programming language, and specifically the request library of Python, which is really handy for interacting with REST APIs. Okay, so the first thing, just using the web browser. And this is the example I had before of the Deck of Cards API, the exact same URL that we built out before. If I just put that in my browser and send it, I actually get back JSON. JSON stands for JavaScript Object Notation. It's just a format, a structure for encapsulating data. And you can see the browser parses that response and shows me the information that came back. My request was successful. I got back a new deck. It's not shuffled. It has 52 cards, and I have an ID, a unique ID. So now I can do additional operations on that deck, like shuffle it, pull a card off of it. So I'm not going to go through all the examples of what you can do, but you could see where you could very easily start to interact with this deck of cards API just using your web browser. And like I said, this is publicly available. You could type the same request yourself, and you should get a similar response. So now what I'm showing, and hopefully you can see this, but the slides will be available if it's too small, making the exact same request in Postman. You can see I'm doing a GET request. I put in the exact same URL, deck of cards, api.com/deck/new. And when I hit send, I get back a very similar response. And with Postman, the nice thing is you can save these requests and responses, and you can build up what's called collections of them and reuse them for later. But another really handy thing is if I click on code here on the right-hand side, it pops up a window where Postman gives me the option to see the code that would correspond to the request I just made. So you can see all these different languages. I mentioned Python before, but I could do it in Go or shell script, PHP, whatever your favorite one is, JavaScript, curl. I choose the request library because there's actually different libraries I could use. And I can see exactly what the code is that I would have needed to written in Python to make that exact same REST request. I can copy that code, and I can paste it into a file here called deck of cards API .py, which is the Python suffix. And you can see that's the exact same code. I just copied and pasted it here. Now I can run it from the command line by calling Python and my file name. And again, I get very similar output, very similar response. So you can see how without really even knowing any programming, I could use a browser, I could use Postman to create these requests, and I can generate the Python code. Actually, Postman generates it for me. And all I need to do is copy and paste it into a file. And then I can go and update these, modify them, reuse them as I want. But it really starts, hopefully, to show that network programming or programming to use this deck of cards API is not that complex. Okay, now the topic is network programmability, so we should probably talk about that a bit. So in addition to the tools that I just showed, like the web browser and Postman, there's a couple other things that make working with network APIs really user-friendly. And one thing is Yang. And what Yang is a data modeling language for describing network configuration and operational state. The really nice thing about this is rather than every vendor of network equipment going off and defining their own syntax and structure and way of defining their API, Yang provides a common modeling language through which to define that state. That state that I mentioned is hosted on the server and that the client can interact with. Thanks to Yang, we have a single modeling language for defining that and expressing it. And the really nice thing is whether you're using a network device from my company, from Cisco, or some other vendor, if they're using Yang, which they basically all do to describe it, it's going to be using the exact same syntax. So you don't need to learn the peculiarities of each vendor's modeling language. Show you what a Yang model looks like. This is IETF interfaces.yang. Now, not only is this using Yang, but it's also a Yang model that's defined by the IETF. So it's a standard model, which is even better now because now you have one way of defining what a network interface is. So this is really great because now when you want to interact with a network interface, it's going to be defined exactly the same way on all vendors' equipment. So here's an example of where standards really help us out quite a bit. The format of a Yang file, you can see it's just a text file. Basically, there's a container, which is the top-level resource that contains all the interfaces. Inside that container is a list of interfaces. Each interface has a unique name, a key, a description, and some other fields. Now, there's a tool called pyang, and what pyang will do is if you give pyang that IETF interfaces.yang file, it will output a tree structure that was represented in that Yang, or that was defined in that Yang file. The nice thing about this tree structure is, if you remember when we had to build out our request URI for the deck of cards API, this tree is exactly what you'll be traversing to build out your network device API. So let me show you how that works. Using this exact same IETF interfaces.yang file, oh, I forgot to mention, we're going to use a protocol called RESTconf, which is basically a RESTful API for interacting with network devices that, where the data is defined using Yang models. So you'll see this will look exactly like the REST request we saw before. You basically have an HTTP verb, in this case get, and we need to build out our request URI. And how we build our request URI out is defined by the Yang file that we just looked at. On the left-hand side is the pyang output, the tree, right, of the IETF interfaces file. What I'm going to do now is traverse that file down the tree so I can build out a request URI to request information about a specific interface, in this case, Gigabit Ethernet 1. The way I build this out is, remember, first I need to specify the protocol, HTTP or HTTPS. So in this case, it's HTTPS. I need to specify the server that I'm talking to. That's done using variables, so I have a host name and a port, and you'll see how these come in later. Then the resource that I want. I'm interacting with the RESTconf API and the data elements, and that's defined in the RESTconf RFC. That's where that comes from. I'm using the IETF interfaces Yang model. I want to request the interface state, and you can see how I'm traversing the tree on the left-hand side to pick up these elements. I want to ask for a specific interface, and the interface that I want has the unique name or key, Gigabit Ethernet number 1. So if I send my HTTP request, what I get back is this JSON formatted information describing my interface. And it's not just any information, it is very well formatted as specified in the Yang model. You can see the information that I get back on the right-hand side aligns exactly with the information that's specified in the Yang model on the left-hand side. So this way you have a very well-understood, well-defined way for accessing information, for retrieving information, and analyzing that information that you can write in a programming language. And I'll show you how you can do that using a couple things. One is, if I go back to this example, remember the host and port? Because I didn't tell you what the server was that was hosting this. So what I'm going to use as the server hosting this is this always-on sandbox, which you can see the server name there, iosxemanagement.cisco.com. The port is, the RESTconf port for that is 9443. And unlike the deck of cards API, you actually need to provide credentials for this one. So the username and password are supplied there as well. Now I'm going to go and use Postman, which we saw earlier, to make a request using what we've just learned to this always-on sandbox. So I build out the request. You can see the get. This is the exact same URI that we built out before, requesting Gigabit Ethernet number 1. There is, if you look at the top right-hand side, there are these things called environments in Postman. And in the environment, I can specify like the host name of my server, the port, the username, and the password. These are the exact same elements that we picked up from the sandbox description. So I put that in my environment, and now Postman can use those, and it's the request that it builds out. I hit the send button, and what you can see is the response I get back. It's a 200 response. And the information that comes back is this exact same data that we saw formatted in JSON that describes my interface. So pretty cool. I can interact with that always-on sandbox. But what's even better is, as we saw with the deck of cards API, if I click on the code button, I can similarly see what the Python code would be that I would need to write to make this exact same request. So I copy that like I did before. I put it into a file called getinterface.py. I just show you what that file looks like. I just copied and pasted it. And now if I execute that using the Python interpreter, I get back that exact same information that we saw in Python. So you can see here, without really knowing anything about Python or how to code, I could use Postman to build up my request. I could get code snippets of what that request looks like, and I can start to write a Python script that interacts with my always-on sandbox. So far, everything I've showed you has to do with reading resources. Of course, with network programmability, you need to be able to create and modify resources too. So with the time that's left, I just wanted to show some examples of that. In this case, I'll be using an HTTP post. And if you remember from the previous one of the earlier slides, post is what you use to create a new interface. In this case, I'm creating a new loopback interface. And you can see it's loopback interface 42 in this case. So my post says I want to interact with the interfaces container, and I want to create a new interface, and you can see the definition of my new interface. And I didn't just make this definition up. The format of this, all the fields I needed to specify were based on what was in the Yang model, right? So I'm just filling in the fields that the Yang model asked for. If I go ahead and send that, I get back a 201 created, which lets me know, hey, it's successful. My new interface got created. Now let's say I want to go and verify that. So now I'm going to do another GET request, and this time I'm going to ask for my newly created loopback interface 42. I hit send, I get back a 200 response, and here I can see that the response coming back is the information I had requested for this interface, right? So it actually did get created. So that's great. Now, what if I want to get rid of that interface? Well, it's as simple as changing the HTTP verb in Postman to delete. And again, I give it the URL for the loopback interface. I hit send. And this time I get back a 204, no content. So 204 is another successful response. So my request was successful. But there's no data coming back because I asked to delete a resource. So the API can't really, there's nothing for it to send back to me. If I want to verify that it's really gone, I can make that exact same GET request that I did before for loopback interface 42. And this time I get back a 404, which you've probably gotten when you asked for a web page before and it didn't exist, verifying that interface doesn't exist anymore. So what I'm walking through here, you can see I actually have on the left-hand side, this is all part of a Postman collection that I built up to interact with this always-on sandbox. And if I wanted to build a Python script instead, I would start to cut and paste bits and pieces from each of these requests, and I could basically build up my Python script, just that easy. Okay, so now the fun part, because I know I walked through a lot and some of the slides were pretty small font. So if you want to try this out for yourself, I welcome you to do that. All the resources I've been using are free and available. The Always-On Sandbox, it's hosted in DevNet. It's free, but you will need an account to use it. If you're interested in creating an account, you can scan this QR code on the right-hand side, or you can type in the URL that was specifically generated for this event, ending in IITRTC19, and that'll take you to this login screen. And in this login screen, you can create a new account if you don't have a login ID. If you have a GitHub ID, you can just use social login that way. You can use Google, Facebook. If you have a Cisco ID, you can use that. So whichever way works for you, that just makes creating your account very, very straightforward. Once you do that, you'll have access to not only the Always-On Sandbox that I showed you, but also some learning resources, so you can walk through in more detail everything I showed you today. Here's a learning module that covers everything about REST APIs, or at least an introduction to REST APIs. Here's one on programming fundamentals, if you wanted to learn how to use Python and using JSON formatted data structures, for example. So some good information about that. And then if you want to learn more about model-driven telephony, programmability, this is using Yang models to interact with network devices. And you can see the bottom one there is using RESTconf. So if you want to get some experience with that. When you go to these, what it'll do is it'll ask you if you want to use your own computer, then you can do some additional setup. And the setup, it works on Windows, a Mac, which I'm using, or a Linux machine, if that's what you want to use instead. So hopefully, seeing the presentation and going through some of those resources, I've convinced you in less than 30 minutes that network programmability really can be as easy as flipping a switch. And I invite you to give it a try. I'm happy to answer any questions, and I'll be around the rest of the day to answer questions as well.
Thanks, Charles. We have time for a couple of questions. If anyone has questions on the topic Charles just presented, yeah.
Right, thank you.
Yeah.
Is this already deployed on all the iOS XEs, or is it only for specific product lines?
No, it's on all of them, iOS, XE, XR, and XOS.
Okay.
Yep.
Is it correct to think this one is like a next iteration of SNMP, because SNMP and there is a MIP, right? And then
Sort of.
This gives you like a REST interface for the tree and traversing the values and stuff like that. Is it?
At a very basic level, yes. And if all I did was get requests, I think it'd be very similar to SNMP. Probably, I would imagine you use SNMP probably for monitoring.
Correct, yeah.
You probably don't use it for configuration.
No, all right.
I mean, the whole reason network programmability came about was really because SNMP, it's not that it's bad, it's just not sufficient, right? It's not good for it's not good for configuration. So really the main value of this is being able to configure devices. Of course, you can monitor devices also. And one of the things I wanted to point out, which I didn't have time to cover in this one, but netconf is another standard protocol for interacting with network devices. RESTconf is probably the easier one. It's REST-like. Netconf is much more powerful and really good for if, for example, what you want to do is configure a new service, and you need to talk to a bunch of different network elements, and you need to configure them all at the same time, and you want that new configuration to take effect only if it succeeds on all of them, and if it doesn't, to roll back. That's very hard to do with RESTconf. It's impossible to do with SNMP. With netconf, it's actually relatively straightforward. I just didn't have enough time to cover netconf in this.
And another question is this only for configuring the ports, or is it, I can model the service, like an MPLS end-to-end? Is it?
You can use it for everything.
Okay.
The one caveat to that is I chose IETF interfaces as my example, and that is one very basic model that has been standardized and is supported on everyone's network platforms. When you get up to higher level network services,
Right.
there aren't not everything's been standardized yet. So what you'll probably find is that to configure that, you'd end up using some Cisco specific. They're still defined as Yang models, but it's not an IETF standard Yang model. It's a Yang model that Cisco defined. And if you were going to be using, Juniper device, it's probably something they defined.
Okay.
So that's the one caveat. But over time, the idea is, yeah, we'll standardize those as well.
Very good. Thank you.
Mm-hmm.
Okay, thank you. If there are additional questions, Charles will be around. You can catch him at the break. I'm sure we'll be happy to answer your question. So a round of applause for our first speaker.
Thank you.
Thank you very much.
All right. So thanks, folks, for listening today. And as Chris said, I'm the Chief Technologist for Red Hat and focused on service providers. And I'm going to spend some time talking about how we use software to actually build and create all kinds of service provider networks. And the best way to do this is to actually look at various examples of customers that are deploying these kinds of things and walk you through the technologies in play. So, kind of what we see around us, everywhere we go, every industry is being disrupted by over-the-top players of all kinds of things. And this collection of technologies is really what's kind of at the heart of where networking is going. And as many of you may know, our company, everything we do is open source, and pretty much all innovations that you look at in any category, artificial intelligence, AR, VR, the new world of serverless, security things like blockchain, and of course, the mobile networks and the edge networks is all, people are leading that work using innovations from open source. And it's interesting when we look at, the world of 5G, sort of our next gen, radios out there, it's not just, about those radios. It's not just about the speed. It's about changing the services for broadband, for enterprise, smart vehicles, telehealth. I can control machines, in mines, and a really important one is we've kind of got a different word for, artificial intelligence. The way I look at it is it's called machine-enhanced human learning. So I'm actually using machines to enhance how we as humans learn and take advantage of that together. Right? We don't replace the human with the machine. We actually combine the two. So Charles talked about open source. And I could put a slide up that has probably, technically it's about 1 million open source projects on the planet, right? I could take one from just, the Cloud Native, Foundation, and it would have all kinds of little bubbles on this slide of about, 1,000 of them, different projects. So when I look at the service provider business, they have kind of categories if we look at the stack of, building a network. You've got the infrastructure at the bottom, whether it's the mobile infrastructure, the compute, the networking pieces, and then kind of everybody's trying to move everything to the cloud, including the service providers. And we all know most of the main projects in that category. OpenStack came along quite some time ago in the IT space. Fairly recently, we've had Kubernetes come along, and there's a couple of interesting numbers on this slide. The 97% and the 95% tells us how fast this world is changing. So in the last few years, 97% or 95% of the code of those two projects have changed. Almost completely rewritten in the last 3 years. So that's how fast these kinds of things are changing. And then what happens is there are lots of smaller projects that come born out of those to go solve different problems, to open up different parts of the stack, right? And these things just try and make it easier to integrate multiple vendors, multiple applications at each layer in the stack, right? We just talked about how we use, REST APIs to, configure network elements. Well, how do I actually manage these things? So we've got projects like ONAP. A very important thing that people are using to complement all those REST APIs and things people use to configure networks is something called Ansible, right? That allows you to automate any process, which includes, a process to set up a server. That's where it started. And now I can use to actually automate the process of configuring a network. So I can actually combine that netconf yang stuff with Ansible and configure entire networks with it, right? And then actually log it, secure it, et cetera. Some other interesting ones as we go higher up into this is as you build these large, services, we actually have to be able to integrate them together. And that's where this group called OPNFV has come along to build out ways that I can interconnect these elements in these architectures, verify them, and make sure that they can be implemented in any global network that's out there. Right? So these are just some of the ones that are in the picture. And as I say, we kind of support them as they fit into different architectures, and I'll walk you through some of those. So just to kind of, think about what serverless is, right? So really, kind of the thinking here is that developers don't really want to worry about what's underneath, right? They don't want to know what hardware is there, what network's under there. They just want to be very happily developing their code at the top of the stack, right? And that's really what serverless is allowing them to do, right? And what you need to have is open APIs down below that, in a platform and open source projects, things like OpenWhisk, the Knative projects, And this allows us to let the developer work way at the top, and I can actually build and run his application on pretty much any infrastructure. And think of it like a utility, right? So basically it's like, the water utility, electrical, whatever, that's really all this infrastructure is underneath. Now, of course, we need to make sure that we have open interoperable APIs all the way up and down this stack to the underlying hardware from pick your vendor, Dell, HP, whoever that makes the servers, right? And the networking piece is underneath, right? But that's really kind of the key to being able to build applications on top of a network and not really understand what's underneath it. Now, we can't forget about the security side of the world. So blockchain is a very important piece for people building financial type things. But in the service provider case, right, their use of this is to deal with people trying to steal services, how I do charging, fraud happening out there in roaming services, people using it for telehealth. And this is where we're starting to take advantage of that. Distributed ledger is really a way that I have a sequence of interactions between these distributed devices that actually say, okay, you have access to this. This is not some centralized place that is a clearinghouse, because it takes actually way too long to clear that, that fraud setup. So this is just a distributed way to actually have that transaction properly secured between the community, right? And so now, in addition to the financial communities that are taking advantage of it, in the service provider space, a lot of them are starting to take advantage of either it's a agreement between, say, somebody in Pakistan and some other country, or it's for them doing interactions for different industries that they want to go serve, right? So I want to go serve the manufacturing industry, I want to charge them differently, I can use blockchain for that purpose. So this is a way to actually configure security into that interaction and transaction for the operators, right? So they're taking advantage of these technologies as well. So now this kind of takes the picture that our customers use to demonstrate what the world of mobile looks like today, and that today is LTE. The world tomorrow moves to 5G. But if we kind of look at this picture, I've kind of made it fairly simple. But on the left-hand side, you got the radios up on the towers, right? They have to come down off that tower and basically become connected to fiber, and then they need to connect into this network. And up until now, most of the devices on the edge of this network are physical appliances, made with software that are, made by different vendors, Nokia, Ericsson, Huawei, people like that. And what we're trying to do is we're trying to open up that radio network so that we can actually use servers at the edge of this network. Because one of the key things as this thing scales out is the cost of appliances at the edge of the network is very, very high to the operator, right? So can I, find a way to do this? So fairly recently, a company in Japan, actually Cisco and Red Hat and a number of our partners built this network in Japan. It's Rakuten in Japan, and they're virtualizing their entire mobile network, right? And they're building a network like this. And what they're doing is they're using effectively cloud hardware underneath for all aspects of this architecture, all the way from the left-hand side of this picture to the right-hand side, right? We're talking, just so you give a sense of the scale of this thing that they're building, in the central sites, they have somewhere close to 250 racks of servers. Right? That's the size of that infrastructure just in one site. I move to the middle sites, I got 15 or 16 racks, and I've got many, many sites. Then I get to the edge, I've got 10 to 20 servers worth of hardware solving this problem. So that big blue line across the top of this picture called cloud orchestration, that's a collection of software from Cisco, NEC, and Red Hat to automate how I configure and change this network on the fly. Right? So they can actually do this automated such that they can spin up a new site and a new service in minutes without sending somebody out to go do it. Right? So this really is changing the time it takes to roll out a new network. Okay. So one of the things that's happening in the world is that as we move to from LTE to 5G, right? The next thing that people are going to try and do is how do I build that new 5G network? So there's new radios, right? And then there's the platform that people use to actually, when you make a phone call, data connection on the internet from your phone, it actually has to get authenticated by some device somewhere in the network. They call that device a packet core. So we need a new version of that packet core, new version of all the devices between your handset and that internet. And so in the world of 5G, we're going to attempt to change that architecture and make it so that I can run that in what we call a cloud native mode. And so there's a project in OpenFE called the Virtual Central Office, and we spent some time building a standardized architecture to deliver business services and consumer services. And now we're going to demonstrate in November in San Diego at KubeCon, a cloud native conference. We're going to demonstrate the next generation of radio technology from 5G in one location, where the new radios are, the new 5G core, and then kind of the complementary 4G, 5G cores. And the world that we're trying to move to is we've been using virtual machines for almost everything, so far, except in the IT space. They've been using containers and microservices for a long, long time. The network side hasn't gone there yet, right? So basically the applications that provide networking are still really either appliances or in virtual machines. And that doesn't, give us the scale we need, doesn't give us the flexibility to actually, spin these things up and down as fast as we want them to do and scale them. So we're going to actually demonstrate this in a cloud native mode at this conference. So we're getting applications from some partners, people like Calum, Nokia, Lenovo are going to actually provide the applications on top of this infrastructure and demonstrate that I can build a cloud native, fully microservices orientation of a mobile network. Right? This is very much the edge of where we're at, because if I go to any of the vendors who actually make these platforms, right, they're still in the lab today with their next generation 5G cores. Because all the 5G that's out there right now, we have new radios, they live, right? We have some appliances that connect them to the core, but the core that they're using today is still their LTE core. They don't have the new 5G one out yet. It's going to come out sometime next year. So we're actually going to show that we can do this in demonstration next month. And if you want more information about sort of what's going on there, you can see the URL on my slide there that talks about this demonstration and the work that the community is doing. Because again, this is a community project, not just Red Hat, but Red Hat and the community showing how do we actually evolve to 5G and take advantage of cloud technology. There's a nice one. Oh, I like that slide. Oh, that's perfect. Oh, there we go. We're going to back it up. All right. So one of the things I wanted to kind of mention is that, this thing we call, sort of deep learning. I lost a couple of slides on the way there. I'm going to see if I can go back. Oh, this guy. Let's go see. Let's go see, and we'll back it up. Oh, I love it. Somehow a couple of my slides died, but that's okay. I'll live. I love it when you put your slides up on somebody else's laptop. Anyway, but effectively we lost 2 slides in the middle of that presentation. So I'm going to talk to those without the slides. You'll see them on the PDFs. So the first one I want to talk about is a customer of ours that is delivering services today for the business side of their life. So basically it's VPN service, mobile services, and that's being all built on virtual machines, as I said. Now, what they've now decided to do on top of that is take some technology from some of our partners, Cisco, Nuage, Ericsson, et cetera, and put those applications into a cloud-native platform, and then deliver their security services, their music services on top of that. And unlike most service providers, the place they decided to actually put that service is not on the Orange network, right, that customer. They're putting on Amazon. So most of us don't buy network services from Amazon, right? That's not who delivers those, right? Because a public cloud is really mostly for web applications and things like that, right? But the reality is that you can actually deliver networking functions, network services. And actually, I think my colleague Charles from Cisco probably knows this number as well, that if you want to go buy a firewall and actually go spin it up, you can go get one of those on Amazon, one of those iOS, Cisco ASR, type platforms. You can actually get one of those, probably about 500,000 of those, running in Amazon today. However, they're configured by you, the enterprise customer. They're not served by Amazon. You still have to configure them yourselves using whatever tools Charles told you about or whatever else you need, right? But in this case, the customer is actually saying, okay, I'm going to deliver my services, and instead of using my private network, I'm going to put all that stuff on top of Amazon. That's what they're going to do, right? So we're going to switch over to AI for a second, and I'll talk about a couple of other customers. So one of the things that people are looking at is how do I actually take the information that's in the network because I got this, you saw those very complex diagrams, got all this data. How do I actually reconfigure this network on the fly, build new services? Why don't I take some, machine learning, functions and actually take that data and use it to actually change how my network configured, how I put up new services. So basically I'm putting effectively an AI platform on top of my network, right? To actually pull the information out. Actually, we talked about this yesterday. I asked the question about whether or not the data scientists were actually just scanning all the data coming out of the network and actually trying to parse it all. Well, the reality is what you need to do is decide the information I want from the network are these things, right? Go get that information, go run your algorithm against it, and then actually use that to reconfigure and reprogram your network. So that's really kind of what machine learning and deep learning allow us to do. Right? And so this is one of those applications where we have a hospital, that has said, okay, what do I want to do? I want to actually improve how quickly and how comprehensive I can actually look at brain scans from many patients in many hospitals, right? So really what they've done is they've said, okay, I want to actually, so while the doctor can typically look at a brain scan in about 15 minutes, in the same amount of time it takes her to do that, she can actually go get the information from a whole bunch of other hospitals. It's securely delivered back to her location across this network, and allows her to actually have visibility to what those brain scans are, so you can say, you know what, I think this patient actually has this very specific issue, right? They can actually treat it a whole lot easier. And so what they're doing is they're taking advantage of compute technologies and programmable networks that actually interact with in a secure manner between those hospitals. Because the other thing about the data in the world of healthcare is that I only need to get the data that is respective of what's in the brain. The data about who it is, what their age is, where they live, all that stuff, that data doesn't come across. It's just the actual information about what's in the brain scan itself, right? So they can actually compute all this information and bring it across, and what they found is they've actually giving much better care, to the patients, whether they're children, adults. This is a way that they can actually take advantage of this technology. And the key here is that it's, we're not, removing doctors, we're not removing nurses, because they still have, the job that we all need them to do, which is to provide the empathy for us as patients. But we're using technology to accelerate and improve how they deliver that service to you and give you better care. And as I say, all of this type of technology is running on top of a programmable network, right? It's using cloud technology, using network technology, using AI to combine these things. So really it's about using software at all layers of the stack to deliver an improved service to you and me. And before I get into this one, one of the ones I wanted to kind of show, it's kind of one I ran into a while ago, is that most of us all have these, and some of us have cars. In fact, there was somebody showed the Volkswagen yesterday on their slide. The one I was going to talk about, I happen to have a BMW. And so BMW has a really nice application in the car called Connected Drive. And they've had that thing for about 20 years. And it's grown over time, and it's needed to get kind of improved. And they weren't actually able to keep up with the millions of cars that were out there that were connected to their network, right? So what they've done now is they've kind of migrated that set of applications, to a cloud-based architecture, and they're running millions of connections a day where people are saying, okay, where's my car? Lock my car, sound the horn, whatever, all those things that you need to do, or connect you to other applications from them. And interestingly enough that, so it's really good at talking to the car, at least as long as the car is connectable, right? As long as you've got LTE in your car and they can find your car that way. But I had my own experience with this particular, recently purchased car. It was a used car, so it wasn't a brand new one, but it wasn't actually working. So I had the app on my phone, and I tried to talk to my car, and it didn't get there. And I could see that, the message going out, getting up to the web, and for some reason it looked like the authentication of me as a person wasn't being recognized by BMW, because I was still in the old system. That's what I learned after, digging into it, is that this old system hadn't been fully migrated to the new system, so they actually couldn't take care of it. But the challenge I ran into was that when I called in, call centers from BMW need some work, right? Because I would get somebody, they didn't understand what I was trying to get at. right? They kept trying to bump me to this person, to that person, to that person. So, the folks that were talking about how to improve call centers and how they can improve our lives, BMW needs to do some work on that one because they didn't actually solve my problem for almost 7 months, right? So that's not exactly, the kind of thing we expect out of, high-end cars, that they're going to solve your problem. They fixed my car, no problem, and take it to the shop, but a web-based network problem, they passed it around and, all over the place. So really important not just to think about the networking pieces, but what's the human interaction with your company that you need to make actually reliable, right? So, if I take sort of that picture of, what I can do to reprogram a network. So what I've got here is a typical way that you could take the network, and the way that we kind of look at a service provider network is in actually three pieces. So most businesses, whether it's a bank, a car company, whatever, they've got really two platforms in their world, right? They've got an applications platform where they run their applications, and they got a data platform where they run all their data. They don't really care about the network because they buy that from somebody else. But a service provider, they've got the data, right? They've got their network along the bottom, could be physical, virtual, containerized, whatever. And then they've got their applications on the right-hand side, whether that's their IoT applications, their billing systems, their analytics, their security applications. All these things run, in the service provider on his application platform. Now, the challenge they have is that between the data that they want to have for their customers and their services, they've got this network, and they got lots and lots of data that's coming off the network. And they also need to be able to, on the fly, change this network without even thinking about it. So that's why they built this system in the middle. Now, what that is a closed loop system that allows them to actually pull information out of the network and change the workflows on the fly, run analytics, run artificial intelligence on it, and then push changes back into their architecture in a consistent manner, right? So this actually is almost like a CI/CD pipeline, a DevOps application pipeline for the configurations of their network, right? So this is how they've taken advantage of artificial intelligence and other application software to control their entire network, right? So this is kind of where, this is the evolution, if you will, of how you actually take a environment that was very focused on applications, for developing things, and apply that to the configurations and the provisioning of a network. This is how the operator is taking, that level of work, because, as I said, they've got all these physical devices, they've now got all these virtual ones, now they've got these cloud native ones, and they need to actually control any one of them in the same way and tie that to their billing system, inventory system, call records. All those things need to be tied together and look very much like a DevOps application space. And if we think about it in real terms for the operator, the way that they actually do these things is even, just like in developing applications. What we got here? Having lots of fun over there. Anyway, so even just like in developing applications, when they go try and put a new service up, they have a development location for that service. They put it up somewhere in development, right? Then they put a test scenario up and say, let's go test that thing, right? Then they put it into pre-production to go test it with a few customers. Then they say, okay, it looks okay, let's actually turn on some serious customer. So they actually have 4 different places they need to test how this network works before they actually unleash it on you and me, right? So they actually have to apply this process to those 4 different environments for any service they deliver. Yes, no. We'll just go this way. There we go. All right. And so one of the things that some of our we're partnering with a university in Boston, and we got this project called the Open Data Hub. And what this is doing is taking a platform to combine data information and machine learning to actually take advantage of these technologies to deliver new services across the same architecture, right? So this allows people to collaborate, build out new services, and that way people that don't have access to, kind of like we just heard about a place to go called DevNet, right, for testing things out that's free and available to you. The Data Hub's kind of a similar thing for letting people test AI relative to networking, right? So that's kind of what we're doing, is showing how that architecture can be built to take advantage of data for a cloud-based architecture. We'll just go this way. And so if we sort of take that, that picture I just showed you and say, okay, I've got this new, data hub for the information about the infrastructure. I want to actually take that, and the architecture of the network is going to change significantly. Most, for now, we've all kind of thought of, okay, the data centers are centralized, the services are centralized, but now, as we push the speed of the network, higher and higher out to the edge, with the next generations of, we've already done it with, cable technologies, optical technologies. We've done access networks of different types, but now we have, with the advent of 5G and the speed it can bring, I can deliver more services at the edge of the network. But what I want to be able to do is take that information, go build that service at the edge, and push that artificial intelligence back and forth across these, think of them as edge clouds, that's saying, okay, I've got a telehealth service, I got an AR/VR service here, I got a content delivery network service here. How do I actually run all these services to all the edges of my service provider network and manage and control those things, right? So really you have to have that intelligence distributed now, not just in that central place where I'm doing certain calculations for provisioning, right? I want to actually control this service at the edges of the network. Right. So this one really kind of pushes the envelope of where the service providers are going next with what they want to go do. So what we've kind of talked about so far in what most of them build is in the middle part of that picture, right? That private on-premise cloud, right? So that's how they deliver a business service, a mobile service. They're going to push that to the edge. But as you can see, they've got their data platform I talked about. They got their applications platform. But you'll notice that they're not going to just sit around and say, okay, Mr. Amazon and Mr. Google, you're going to go take my customers. He's going to actually take advantage of public clouds to deliver his services, right? He's also got, for people that's still running on bare metal machines, he needs to be able to deliver some capabilities there. He's also got his own network. That's kind of the one of the very far right. That's the physical one, and he has to take advantage of programming technologies, API gateways between all of these clouds, all of his platforms, and actually run that management as code between his pieces. Right? That's what he's really got to be able to go do. Right? So this is really kind of the evolution of their architecture. So it's not just his network, but he's actually interacting with public clouds, as well as his enterprise customers, as well as you and me across this architecture. So you can see that the programmability of a network in the context of a service provider is a huge undertaking to them as the evolution of physical to virtual to cloud native happens. And I think I'm just about done. And so really kind of what, the building open platforms like we just talked about, it's really about being able to deploy any application anywhere, right? People want to have access to whatever they need, anytime, anywhere. I want to be at the beach getting services. I want to be, in different countries getting services. And, if I can program these things in an open fashion, I've got the freedom to actually, and the confidence to actually accelerate how fast I deliver them. Because really the key thing to the service provider and almost any business is he who gets there first and fastest gets the most revenue, right? So if you actually don't get the market quickly, you actually lose opportunity. Your competitors actually take the business from you, right? So they need to be able to do this very quickly and be confident, and they got to be able to secure it, right? Make sure it's secure for all of us to use, and do it at scale, right? And this is really kind of the thing that Red Hat's working on to drive the, the reduction in risk and the ability to drive these applications that change the lives that we live in today. So that's what I had to share, and I'll be happy to take questions. Thank you.
Okay, thank you very much, Ian. We're right at the edge of our time here, so unfortunately we don't have time for questions at this point, but Ian will be around. I'm sure he said some things that have piqued your interest, and he'll be happy to talk to you in the sidebar. So thank you very much, Ian.
All right, thanks.
Do you want to use yours or? Okay,
Send
that's
it.
fine.
Well, I mean, it would work, but you don't have a
Right.
PC, do you?
Did you send your deck in ahead of time? Okay. Bear with us a second. We're just pulling up the presentation file.
It's on the internet, right?
Where do you want to go? No, he's just accessing his file off the internet. Okay, as we get started here, I wanted to mention that Anthony is the CEO of SignalWire. He and his team have an exhibitor booth in the hallway here, so as you pass back and forth to breaks and meals, please stop and say hello and make an inquiry. Anthony is going to be talking to us about software-defined telecom. Please welcome Anthony.
Hello. Can you get the full screen to work? Full screen? No. Guess that's the best I get. Alright, that's good enough. It's not that exciting anyway. Pages. This is going to be real fun. Okay, so hi, I'm Anthony Minasali. I'm working here with a little awkwardness, so I can't fit my slides on the screen, but we don't care. I'm the founder of the Free Switch project, which is a telephony stack that we started back in 2005, and I'm also the founder and CEO of SignalWire. I've been a long time open source advocate. It's actually better to make it smaller. There, let's do that instead. That's weird. So, when we first started doing telecommunications, it was a huge advancement in how we could communicate. So we would have a lot more trouble telling people information, a lot more miscommunication. It was a really great advancement from what we already did. It took a lot of effort. We didn't really have that many materials to work with back then, but somehow we used ingenuity and a lot of engineering to come up with ways to interconnect nearly any two spots, with each other, and that was like a big difference from how things were before. And that slowly evolved over maybe 30 or 40 years. The density became easier. Entire buildings were replaced with a device like this, condensing a lot of telephone calls into a circuit that allowed you to do all kinds of really cool stuff. But the problem was that it was still confined to hardware, and it was very, very rigid. So you could get your telephony to scale, but it's really kind of the paradigm was still stuck at a very simple place. So really on the outside, the only thing you needed was this device. There's one in nearly every location. You could just pick it up. The only interface was dial tone coming out of it, and you could press buttons on it. So, somewhere around the 70s, we started to standardize on this kind of interface for everyone. And we still are pretty much doing that now. Like, no matter how cool our phone is on our desk, it kind of just looks like this. It's a plastic thing with buttons on it. And all you have to know is to pick it up. And we even pretend to be dial tone for you when it's not necessary. So it's kind of like, due to the simplicity and the longevity of things, we've been really reluctant to change anything about it. What got exciting for me was when the world of telephony collided with the world of computers. The first time I realized that you could plug a telephone circuit into a computer, and then the resulting telephone calls made to that telephone circuit could wake up the computer, that was like really great. And that's like a big change, again, from what it was before that, because the possibilities were endless. There just wasn't really any progress on the whole idea. It was very new, and it was just like there was a proof of concept that you could like wake up a computer hardware with a telephone line. Then came open source. When I first got into this, I was like, heard about Asterisk. I'm like, Asterisk is cool. It's like an open source PBX. Really? I can do this? And it was really great playground for me. So I got involved in it. I started trying to build things. One of the first things I was really playing around with was plugging this physical world into a computer, because that was what I was obsessed with at the time. So I put in, plugged in a phone in the back of my computer and my own little phone company by myself, and then I plugged in eventually a huge circuit, 600 phone calls coming into the computer, and did all kinds of really cool stuff. And I got to a certain part where my ambition outgrew the world that I was in. So open source didn't totally save the day for me, it kind of gave me a playground to work in, but it really, the existing open source telephony at the time was limited in the scope of what I really wanted to accomplish. So I got inspired even further by being able to make these experiments with the existing open source. I still had a lot of work to do. So eventually, after 3-4 years of putting some significant coding into Asterix, I was a contributor and a committer and did a lot of bug marshaling along with my team. I decided that I should just stop trying to work against the grain and start from scratch and truly dive into the world of open source by creating a new project. And it's called FreeSwitch. And this is back in 2005. The main purpose of FreeSwitch is to try and take what's left in this physical world and make as much of it as software as possible. Because the more things that are made out of software, the more you can manipulate it a lot easier. It's a lot harder to manipulate hardware. You have to make a new version and install it everywhere, especially at density. It makes more sense for hardware to be designed at a lower level to just move traffic. Like making networking equipment more fast and more powerful is way better use of time for hardware than trying to make the specific telephony hardware, especially the way it is these days. Kind of similar to like video games or anything else. Like you want to, like the medium that it travels over is way more important than the content, because once you make it into software, it's very easy to port it to different environments. And we felt the same way about telecom. So a group of us, Asterix people, decided to, just start over and see what would happen. Like start an empty directory, type code and build a core, and like just kind of reimagine exactly how telephony should work in a software environment. So that's what we've been doing for a really long time. And since we started doing that, things have changed a lot. When we first started, everyone used SIP, but only a certain level of understanding. There's like kind of like a club of people that knew that SIP was really useful and made things out of it. A lot of the carriers at the time were like terrified it was going to put them out of business, so they'd say it sucks and make fun of it. And there's like the internet conditions were really bad, so sometimes the quality would suck. A lot of people tried to rush to implement their different versions of it. They kind of had like an inadequacy with the spec and started trying to make it do everything to compensate for failures and the foresight in the design. It kind of got into a big mess, but that whole 10-year period when like SIP sort of took over. Like there was H.263 at the time when we started FreeSwitch, but SIP was like really the driving force that started making people believe they could use software telephony. There's like 1 million SIP apps now. And FreeSwitch was able to basically trunk like large volume of SIP traffic. So people were starting to build companies out of it, using it for things like ISPs, like taking like 2,000 calls at once and trunking them over to somewhere else and then splitting them off into like 10 other smaller ISPs and a lot of different things like that, like the true nature of a soft switch. So we had a lot more ambition than just being that, but it was a very popular thing. While we were building this, a few industries started to pop up, ancillary, that relied on software-defined telecom. Asterix was a big part of our past, so we're really like glad that we got to know it, but we sort of outgrew it. And around the time that we started FreeSwitch, we were a little too early for Twilio, who decided to build, their infrastructure around Asterix. But they took it about as far as you can. Like they made it really easy for people to understand some of the stuff that we took for granted. So consider that like a really good kind of first chapter in the whole story. But now you look at the way that some of these things are designed, and like we feel that the way these diagrams look, the software that was used for them kind of dates the technique. So we're seeing a lot of this, normalizing things in the REST because HTTP 2 was like really cool, and you could try and leverage the web apps by scaling. HTTP has graduated to 3 now. There's a whole new future of how we can do some of this stuff. And we really kind of, want to stay ahead of the curve. That's what we've been doing this entire time. So it's getting a lot more challenging now as the mainstream starts to pick up adoption for like understanding what voice over IP is. One of the things that we find important at SignalWire is to continue the open source foundation that we're built on, which, the FreeSwitch project has just moved into GitHub. SignalWire also has a whole bunch of other APIs and stuff on their GitHub page for various languages. And there's a community for Slack that anyone can go to that URL at the top there and just self-join our Slack channel. We have like 2,000 people in there, and basically everyone kind of interacts and tries to build stuff. And we're trying to really combine the idea of solving business problems with innovating in the software space. So kind of in the same way that I was really excited when we combined the telephone with the computer, now we're combining the computer-defined software with actual programming. So now the idea to make the programming so easy that anyone is able to interact with it is a new challenge. So we have very complicated technology, video conferencing, and live WebRTC stuff. And WebRTC itself is a really low-level API, and everyone is struggling to understand it. So we feel sort of the need to figure out how to normalize those things, make them so easy for you to use that you can focus on your own desired application rather than having to learn the in-depth, repeating these processes of understanding what WebRTC APIs are and how to host a server and how to scale something beyond one server, which is a really big problem. A lot of people will prototype stuff on the one machine, show it to everyone, or they think it's cool. I learned this lesson myself a long time ago, and then you go to scale it, and as soon as you throw it, how are you going to have it on 2 and 10 and 100 machines? And there's lots of those problems that we'd like to solve for people. The most important thing that I think I like to get across is that today the mobile phones are no longer actually phones. We still call them that because that's where they evolved from, but they're not at all. They're just kind of an analog for what used to be a phone. Because really everything now is a computer. Every single thing that we touch with it has a glowing screen is a form of a computer. So we have our laptop, and we have Alexa device, and we have our phone that we still call a phone, but there's not that much of a difference between them anymore. They're internet-connected devices that have communication input and output on them. But because of that, everything actually is a phone. Again, going full circle, because now everything is a phone. This thing I'm standing in front of is a phone. That thing in my pocket, everybody's got 1, 2, or 3 devices on them that we could make a video call on or communicate. And there's a lot of work to do to make sure that we segue from the large amount of kind of legacy stuff with what the new stuff is. And kind of one of the things that we'd like to do at SignalWire is to balance that and not get obsessed with, looking backwards and only saying, what we call a CPaaS today is just kind of making it easier for you to interact with the phone network, we're accepting the phone network as should stay. And we really think that we can replace the phone network with the internet. And we've already been trying to do that as a world for a really long time, and there's a lot more work to do on it. So the entire reason that we do all this stuff is we'd like to kind of get rid of this antiquated telephone network and the concept of phone numbers. We can leave some of that around in a new kind of virtualized form, but there's no need to just peddle old school stuff. So at SignalWire, we do sell old school phone numbers, and we let you text over them and that kind of stuff. But we're not too excited about it. We just do it because you're probably going to need it in whatever else you're building. And so we're going to be working as hard as we can to make things so that everyone in the world can use our stuff, not just developers with a degree in computer science, which is really kind of one of the things I didn't realize when I started writing FreeSwitch was that I was taking something that was impossible and making it so that it was possible, but it's still really complicated because we catered to the needs of nearly anyone that asked. We grew really powerful, and we started using, different kinds of configurations to segregate out behaviors. And sometimes, like one person's idea of a bug was a necessary feature for someone else, so we'd have to make parameters around it. So we can control the behavior to the degree that's like just learning how to operate a voice over IP network in the software is almost equally hard as any other thing starting from scratch, like the entire computer science degree. So one of our goals is to just take that stuff and balance it so that you still have open source software and tools to mess with, but you also have like the really hard problem solved. And there's actually a value add from, you know, the amount of work it takes to do the R&D and hire a huge engineering staff and host a bunch of servers versus the stuff that we want to do. So that's really kind of the whole purpose. And I encourage you to visit us. Check out FreeSwitch if you haven't heard of it before. It's on GitHub. It's really easy to find now on GitHub/SignalWire/FreeSwitch. And maybe next year we'll have some even more exciting stuff to talk about. But for now, that's what I have to say. And if you guys have any questions, now's a good time.
Okay. Thank you, Anthony. Questions for our speaker? Okay.
Too thorough. Happens.
You answered all the questions in your prepared remarks?
Yep.
So there you go. All right. Thank you very much. Okay, a little housekeeping. This was the first of 3 sessions in this track. We're coming up on our morning break. There will be refreshments at the other end of the building here. Again, please stop by, see the exhibitors, including SignalWire, in the hallway as you pass over there. There is a keynote coming up from 11 to 12 a.m. That's in the McCormick Ballroom next door. So please join us for that. Then that's followed by lunch, and we are back here in this room for this track at 1 p.m. for 3 more speakers. Thank you very much for your time and attention, and we'll see you back here shortly.
service, the first stack built on top network. V2APN is the world's first
knocked it off. Yeah. When he comes back.
Ah.
I just woke it up.
Ah. Okay.
All right.
Ah.
Okay, folks, why don't we take our seats so we can start on time? Welcome back to the second session of the programmable telecom networks track. We're introducing our fourth speaker in the track. Our next speaker is Steve Way. He is CEO of Top Network. Steve is a successful serial entrepreneur that's been involved in companies including WebEx, Sendwave, which was sold to Huawei. Steve has founded Dingtone and operates other apps including CoverMe, Sky VPN, and so forth. So Steve will be talking to us today about decentralized cloud communication networks. So without further ado, Steve, go ahead.
So, hello everyone, good afternoon. My name is Steve, CEO and co-founder of Top Network. Today I'm going to introduce a decentralized communication network. So we are seeing a lot of communication services, but it's all centralized. And we are building a decentralized network with blockchain technology. So Top Network is a network, is a decentralized open communication network that provide cloud communication service like messaging, calling, VPN, streaming, all those kind of cloud communication service, plus storage service. So basically, Top is like AWS for communication. It's powered by first generation blockchain technology. For example, like end-to-end encryption, decentralized. So it's secure, private, and unstoppable. And it's censorship resistant. So nobody, even government can stop the network, censor the network. And any application built with the Top network is also secure and private. Let me introduce the architecture of Top network. Let's see from the bottom, it's a network layer. So it has the P2P communication network, has the P2B storage network, and it has a blockchain network. And the network, the server in the network is provided by the community, not from any centralized organization. So there is no V. It's by contributed by the community. Any individual person, any server, any computer, laptop. And in blockchain world, we call them miners. In traditional world, we call them service provider, right? But in blockchain, we call them node and miners. And beyond that, on top of that is the service layer, so that we can see the communication service it provides VoIP, RCS, VPN, CDN, and IoT plus storage service. And we also have the API and the SDK stack. So people can build a communication apps with the SDK. For example, you can build a messenger app with the SDK. That's the whole architecture of top network. So let me talk about the core value of top network. It's very different than the centralized version, centralized network. First of all, top provide a very low cost service. The core reason is because it's decentralized. So there is no middleman. Think about it, the AWS has a 60% profit margin. That's the profit. And the top is decentralized, so no middleman. Everybody contributes servers, and they don't take the profit. So that means the service is very cheap comparing to the centralized version. And so that's a low cost. Secondly, it fixes the privacy and security issue. We all know, Facebook today, even today, is still doing a lot of evil things, right? And WeChat, a lot of Chinese person use is much more worse. But the top network, because it provides end-to-end encryption, and the user profile is stored on blockchain instead of installed on the centralized server. So nobody can resell your data to third party. Nobody can hack your communication, monitor your communication content. So unlike the centralized version, a messenger app built with the top network, there's no way to monitor your chat message. Look at the WeChat and the Facebook Messenger, WhatsApp. They can see you. They can view your message. They can archive your message. So it's horrible. So we want to fix the privacy and security issues over in the communication industry. Last, the top network is built with the RCS communication protocol, so it's interoperable. And any application built with the top is interoperable. They can talk to each other. So let me introduce some use cases and what kind of apps can build with the top network. So essentially, you can build any kind of communication apps or any apps with a communication feature with the top network. For example, you can build VPN apps, messenger apps, streaming apps, and storage apps, video call, audio call. And let me introduce the first decentralized communication app built on the top network. It's a decentralized VPN. So the name is a Beta VPN. So this is the world's first decentralized VPN app. I have a video. Let's watch that.
VPN, a decentralized VPN service, the first app built on top. VPN is the world's first decentralized VPN blockchain, powered top network, unstoppable mesh VPN network, contributed by users like you, other community members. Top network is a decentralized open communication network. It provides VPN, messaging, calling, CDN, IoT data sharing, storage, and other decentralized communication services powered by blockchain 4.0 technology. Top network includes a mesh VPN network that interconnects thousands of servers and millions of user computers. Each computer acts as a VPN server, as a node and receive tokens based on the bandwidth of the contributors. We call it proof of bandwidth, aka P2P. When a user uses a VPN service, the app connects to node top network. Top network will report the node based on its bandwidth contribution. How can average you
The BT VPN app is the only VPN survive in several countries, like Iran, like other several countries, because it's built with blockchain technology. So it's very, very difficult to block it. So we know build a communication app is not easy. I have been built many communication business. Started from WebEx. I was the first engineer of WebEx, so I essentially designed the web conference architecture for WebEx. And later, I was doing the video conference business, and I sold the business to Huawei 10 years ago. Later, I co-founded a company, was doing messenger, VPN, those kind of business. And as we know, build a communication app is very tough. You need to build a communication stack as a back-end communication software, and you need to deploy servers. You need a NOC to operate the maintenance of the network. It's a difficult task. But with the top network, developers is going to develop apps very easily and quickly. The developer just need to care about the user interface. For example, with the top network, you can build a messenger app in a few days. Traditional, maybe you need 1 year or several months, and you need to hire a lot of developers to build audio, video codec, communication stack, and backend stuff. It's a very massive job. And so it can save a lot of cost for the developer. That's the benefit to building app with a top network. And let me introduce some core technology in top network. As I said, top is a decentralized and a trustless network because the network is from the community, not from us, not from a single company. And so it's become very difficult to, for example, for QoS and security, billing, and ledger. And last session that the professor there, he teased the QoS stuff, but QoS is very difficult on decentralized network. Let me go through one by one. First of all is the QoS. So top is essentially a decentralized SDN. It's a software-defined network. And we have a decentralized control and hierarchical decentralized control that can have an abstract view of the entire network. It's still decentralized. So it knows what's happening inside the network, even it's decentralized. And second, we invent a technology we call the smart routing. The system can automatically find the best routing path in the network without pre-configuration. Last, we have the proof of capacity or proof of quality. What does it mean? Because the server is not built by us, so we don't know the quality and the capacity of the servers in the network. So we have to implement a decentralized system to detect, determine, and modulate the capacity and the quality of each server. The system is automatically doing this. There's no NOC is monitoring the quality and the capacity of the server. Nobody is doing that. The system is intelligent, monitor that. And security. So, the node, the server is from anybody, right? And we have to assume a server could be evil. You cannot assume the server is good. We have to assume it's bad. And in this situation, how we ensure the security? First of all, we have to adopt the end-to-end encryption. So entire communication session is encrypted, and nobody in the middle can hack the content. For example, say there is a server is from an evil government, and the system chooses that server to serve the users, and even in that situation, that server cannot hack into the content. So that's end-to-end encryption. Secondly, the traffic obfuscation. What does it mean? So even the traffic is encrypted, but people may find the pattern. For example, say you visit a special website, it has some patterns. So some evil servers can analyze the pattern and they can filter the traffic. Means you can block you. But we use the traffic obfuscation, so the traffic pattern is hidden. You don't know, what kind of traffic is sending. Last, we are using VRF. VRF is a blockchain terminology. It's called a verifiable random function. So it's used to choose the server to serve the communication randomly. It's truly randomly. And nobody can control the selection process. So it means each communication session, the routing path the server randomly chooses. So make sure it doesn't go a fixed path and somebody in the middle can monitor the communication. So what we're doing, essentially prevent the attacking from the malicious nodes. And billing. So how do we log the accurate billing information in a decentralized network? Remember, a node could be evil. They can overstate the workload, the contribution. In a centralized system, you have the billing system, right? You log all the usage. The usage is from the servers, the communication servers. But in decentralized system, there is no centralized billing system, no centralized servers, no centralized database. And each server can report their contribution freely. They can say, I serve 10 megabyte data. Another server say, I contributed 1 gigabyte data. They can state any contribution they like. But the system needs to design an algorithm to figure out its true usage. So we have to use several servers in each communication session, and each of them have to reach a consensus. For example, say there's 3 or 4 servers in this VPN session, 4 relay servers. If each of them report a different usage, that means this session will fail because one of them is cheating. The consensus means the 4 relay servers report almost the identical workload. That means this session reached a consensus. That's the exactly accurate usage information. And this information is recorded on the blockchain. Because you know that you cannot change the blockchain information, right? And because it has the consensus from multiple servers, so it's accurate information. Last one is the payment system. So in this peer-to-peer network, decentralized network, there is no centralized company to receive payment. For example, your communication apps use top network. You pay the node automatically, peer-to-peer, not pay to us, pay to the top network company. We are not in the middle. So it has to settle down automatically. And remember, communication service, you guys are all doing the communication business, right? The transaction is huge. And we know blockchain is super slow and very expensive. For example, the first generation is Bitcoin. I know everybody knows Bitcoin, right? Bitcoin, the transaction is, we call the TPS, is only 4. So every 4 seconds, it can only process 4 transactions. And the confirmation latency is up to 10 minutes. Have you guys sent any payment use Bitcoin? You send a Bitcoin payment, you need to wait 10 minutes to settle down. It's so slow. And it's expensive. Each transaction costs about 10 cents. That's the first generation. The second generation is Ethereum. Anybody heard of Ethereum? Okay, good. Yeah. It's getting better. So TPS include 15, and latency reduced 1 minute, typically 20 seconds, and the fee is half a cent. But half cent is still too expensive in the communication business. For example, you send a message, and the payment, the transaction fee is half cent. It doesn't make sense, right? So we have to develop a fundamental different blockchain that can handle transaction on blockchain. So it has to be a radical new blockchain platform. So that's what we call ourselves the first generation blockchain. It can handle million TPS. So it has the same capacity like a centralized billing system, centralized payment system, and it's close to the performance like Visa and MasterCard. It still has to be very cheap to process the payment. The transaction fee has to be almost zero, 0.00001 cent. So we invent a very novel blockchain architecture we call the three-layer ledger. So typically a blockchain has only one layer ledger, like Bitcoin, Ethereum, and it's not work in the communication industry because the communication industry is super high volume. So the three-layer ledger is we have the main chain, and we have the service chain, we have the off-chain ledger, three things combined. That's the two blockchain stuff, so I'm going to skip this part, those chain stuff. It's very difficult. So our mainnet is already going live, and we are basically the highest performance blockchain platform today on the market. It's designed to process super high frequency transaction like communication, like gaming industry. So Bitcoin and Ethereum is designed for financial industry. Payment, you don't need a lot of transactions. So our mission is to design make a public infrastructure for communication industry, and it's AWS for communication. And you guys, do you guys know the IPFS? It's a decentralized storage layer. It's getting a lot of adoption, and we are going to be the decentralized communication layer for the public. Yeah. That's all. Any question?
Bringing you the mic.
How does it work with the fact that each node on that network needs a round trip, either on a fixed network or wireless? So if my computer is one node, then everyone else has to, the data has to come into my my PC and then go back out again. And if it's on the phone, the same thing. So you end up with sort of like the network being in, out, in, out, in, out, because you have to do two trips on the access network for every device, which will add massive latency.
Yes, yeah, good question. So remember I mentioned that we have the smarter routing technology. So basically, let's say, we have two person, they start a VoIP session, yeah, and they need to make a phone call, right? And there's a client A and a client B, and let's say client A in California, client B in Chicago, and so they need to find a servers, several servers, and the best one to serve the communications. And for example, your server may be one, but if they find another server in data center, it has much better performance and capacity. So they will choose that one, not you. So they always choose the best servers for the two clients to the users. Yeah, it's randomly, but it's randomly because there are so many servers. But they are going to choose the best ones, or some of the best ones. Yeah, and this server has the minimum latency and the biggest bandwidth. Yeah.
What about the latency of the payment mechanism? So presumably there's some sort of back and forth before someone goes, yep, that person has enough money to pay for that connection. You end up with 10 people involved having to pay or receive for every single connection.
Yes.
And how long does it take to set up and agree and clear all that payment before the call or whatever can occur?
Okay, let me go to this one. Right? So each relay server, so this is like a server, right? This is 4 servers. Yeah. So this is a meeting session, right? Yeah. And the traffic goes to this server, that server, these 4 servers. And each server will report the usage. And you cannot cheat the usage because the system has an algorithm to detect that. So in the end, for example, this server contributed 10 megabyte data, and this server contributed 5 megabyte data. And there is a price for the communication. For example, say 1 token per megabyte data. That's the price. It's not free. The network is not free. I think this part gets confused. No. Yeah. No. Yeah. So you have to pay the tokens for the network. It's crypto. Not a fiat. Not a fiat. It's crypto. So remember I mentioned settlement on blockchain means use crypto. Yeah, fiat currency cannot support that. Definitely no way to support that. Okay, thank you.
Any other questions? Thank you very much, Steve.
Okay. I saw it earlier.
Kelly's going to be talking to us about 5G delivering programmable networks.
All right, Chris. Yeah. Where's that at? There we go. You bet. All right. Let me get back there. Okay. All right. All right, so I have to talk about 5G programmable networks after Henning's discussion about QoS and whether or not he believes 5G network slicing is something that'll work. So let me try to convince you that it will work, but maybe some differences in the way people are thinking about how to do that. First and foremost, when we talk about 5G, we have to talk about how's it being used, all right? And this is kind of a classic discussion of it, the massive machine type communication, the critical machine, the critical machine type communication, and enhanced mobile broadband categories. But when you think about those, what is the use cases that we're delivering within each of those categories? What are the people trying to accomplish in terms of those types of use cases? And when you think about it, it's the smart agriculture, it's the AR, VR, but then you have to also look at how do I deliver that, right? So I've got classifications of these uses, I've got description of what they're being used for, but then each of them have characteristics that must be accomplished in order for that service to be delivered. And that's what I want to talk about is 5G being able to take those classifications and services and deliver them. All right, the way we do it is network slicing, okay? It is to address the business drivers, but if you look at it, you have to look in terms of, you know, that driver being mobile, whether or not the application has dependencies on latency, the availability of that service and the reliability of the service offering, as well as the intensity of the interaction and the volumes of data that's being driven. So when we look at each of these business drivers, we have to look about, you know, how is that need being delivered? Where do we actually get that programmability into the service in order to make sure that those requirements are addressed? And when you do that, making it so that it's flexible, fast, and actually make sure that you don't impact others when you do that. So one of the things we've been talking to within Ericsson is network slicing and distributed cloud go hand in hand with 5G. And the reason for that is because of those various requirements, you're going to have sites placed at different locations for delivering on those requirements. And you know, those requirements are not just the 5G network functions, but they also have to be married up with the application or the use case that we're trying to drive toward. So for example, in the case of the automotive, you know, you have connected car, you want the network function and the radio function to be very close to the car in order to get to the, you know, critical apps for them. And that might be more around the self-driving apps, for example. All right. When you start to move toward the center, you can have more latency, you get a little bit more scale. And what you are able to do then is address another set of use cases. So what we see is kind of the spectrum for each of our targets, having a set of VNFs and applications that may be close or may be far in order to deliver that service. They may be on edge sites, they might be in regional sites, or in the core. But when we look at that, you know, it's driven by network characteristics that are needed by those services. So for example, when you look at things closest to the application, it's usually, you know, the desire to make sure you have low latency, maybe a high volume of data required around that device, or that it needs intelligence in order to fulfill its operations. So you need to move that out closer to the edge. Conversely, you know, if you can pool the resource, you know, then you have a better use of the overall resources, and you can gain in terms of your overall OpEx and CapEx. Kind of an example of distributed cloud where you can make use of it for two use cases. For example, the robot on a smart factory floor, you need the data center at the edge. Well, what's that data center, you know, need to have? One is the radio access. Two is a user plane so that you can, you know, send the data somewhere. And then three is the application itself, you know, to make use of that data and run the robot. However, because you have radio access out there in that smart factory, you can also, you know, handle the mobile broadband case, Well, in that case, you still have the RAN, but now you're more dependent on the data center for the connectivity of that application, maybe to an IMS server in order to fulfill a voice. Okay, so depending on how you're using the network and the service you're delivering, will place those application servers and those network functions in either the edge or in central sites. However, one of the things that we have created with 5G Core is an explosion of network functions, right? And in doing so, create a bit of criticality for making sure we have automation of these functions. So if you look on the 4G side, we had kind of a rather simplistic access network. Then it would have a gateway toward your internet, and you have a simple subscription, right? Now that we want to do more, we've actually decomposed the functions so that you have, an access on-ramp controller, and you have a session controller, and you have user data. Well, all these have been decomposed so that you have APIs you can interact with, but in delivering some of those core services, you have to stack those up for the service that you wish to deliver. Now, one of the things I think becomes important in 5G is a couple network functions in particular. The network resource function, which basically says what do you have, what states are they in, and what's their utilization. So do I need more? So do I need more AMFs? And where is that AMF? The network slicing selection function, that helps you, decompose your network into where are those resources available to you. So it works very closely with the network resource function, which is really good for us in the sense that now that we know where things are, and we've got a mechanism by which we can define, those use cases and describe a slice, we can take advantage of, some level of automation from these, right? So some of the automation that gets supported by this is the registration of a new service, all right? The notification if a service fails, the upgrade of those services. So this network resource function becomes essential to your ability to know where the resources are and deliver those resources toward these use cases. One other thing that's offered with the 5G architecture, and 5G core architecture, is the network exposure. So now you also have a means by which you can communicate toward other application functions. And what that does is it allows you to add on, so to speak, to those services you have delivered. And what's the beauty about this is this gives you the APIs in which you can construct further services. Now, when we look at the automation to this, though, you have to have some overall orchestration across the patch. Services in the 4G world were relatively constrained to a couple data centers, a few data centers, and it was treated more or less like a big monolithic set of functions together to deliver the mobile broadband service fundamentally. Okay. Now, as we talk about delivering on a series of services, cutting across the network nodes, now you have to look at how do I coordinate that? How do I make sure that the different cloudlets, you might say, are visible to that user and that service? And why is that important? Because when we look at the slices, they have different demands, different needs. So for example, on the public transport slice, this is one where you may want to say, hey, I'm actually going to try and segment my network slightly, isolate it, make sure it's managed almost as if there was a full separate network, right? And when I do that, I'm going to dedicate certain functions to fulfill that role, right? So everything in that slice is now dedicated toward that user. However, I still have some, things that I can share, right? And if I look at subscription data, for example, and policy, I can share those across multiple network slices. So now I have the opportunity within my large central data center on the control plane to actually manage across the number of slices and use that resource more effectively. When I do that, I now have subscription control. Now, when I also have the opportunity to decide is where do I want my network functions to reside? Is it in the national data center, or do I want it at the local data center? So when I talk about the manufacturing slice, that manufacturing slice, because of maybe smart or smart factory, I want to make sure I have network functions out in that edge so that I can keep my factory running, have good responsiveness, and then also with this UPF, go to my local app that controls my controls of my factory. However, I also have users that are off the mobile broadband network that maybe are going to make use of the radio access there, and find myself working as just enhanced mobile broadband, but for a certain class of users. So they're making use of the national network functions. Okay, so with this, it creates complexity, but once you define the slice, that's actually where the complexity ends. You've got now a service that's end to end, and you can put users onto that service. Okay, and give you a couple examples of creating that service. Here's where you have to have orchestration come back into play. So one of the things I will warn people on is you can't do 5G network functions without some plan of orchestrating those network functions, all right? And when you do that, what you're going to set up is I have a definition of what my service is going to be. That's one. Two, my VNFs have to be instantiated. Three, I have to decide where that is. So in this case, it's cluster 1. And 4, what are the functions that are going to exist in that site, right? So that's all orchestration. That's basically taking a template of what that network service is going to be, deciding where those network functions lie, and putting them into service. And 5, completing the picture, because I, as an operator, have this network slice. I have to make sure that those users are users authorized for that system, right? So take care of some shared network functions back at the ranch. Okay. The enhanced mobile broadband slice. So again, I defined the slice. Now I have a shared AMF, or access management function. That's already up and running. 3, now I decide what else has to go with that. So that's the enhanced mobile broadband slice at a VCP edge site, right? So I'm bringing up a user plane, I'm bringing up a session management function, and then finally completing that slice with some shared network functions, for managing the subscribers. And then finally, my massive IoT slice, this being a transport scenario. I'm out at the edge, and again, defined the service such that I'm going to share the access. I'm going to now instantiate in another edge site my user plane in session for the massive IoT function, and then put those users into the system as well. So you can see, by using some logic here, describing a set of services that I want to fulfill, architecting and organizing your network functions to be placed to fulfill those services, and then wrapping it up with the orchestration, you can make this a programmable network, right? So now what you have is the opportunity to add more users into each of these slices. So I think what we have the opportunity to do with moving this this forward is to take and extremely program how we're implementing the life cycle of VNFs, the slice management of those network functions, and then simplify the implementation for services toward the users. Right? So 5G has that promise. I don't think of 5G as working toward a specific QoS. I see it more as constructing a service and a set of conditions so that service can be fulfilled. All right. So the opportunity that comes for the service providers is not just simply mobile broadband, but now I start to address new use cases. Now, I think when we kind of take this example of the network slicing for railways, you're going to start asking the question, who's providing that service? I think there's a lot of debate on how these will actually end up being realized. Right now, we've talked about 5G mainly being delivered by the service provider in the sense that they've got the spectrum, the RAN, and the core network is usually theirs, all right? But we're starting to see some very interesting things happen where, you talk about private LTE. Well, do you sell the box and, that box is served by that user and you provide some other level of services back at the service provider? So I think the story is still out on, where is this best served? How is it served? And then also the constellation of, I'll call it cooperators to deliver on that service. I kind of almost relate this toward the PBX business where enterprises wanted to have control. They would buy these PBX systems, but you still had to have interconnections with the operators, right, in order to actually fulfill your business needs, right? So now, what's that parallel? Well, now I've untethered myself. I still have a lot of the same, desires to have a closed user group that's just my company. I have a desire to make sure that it interacts with my systems. So is the solution, carried fully by the operator? Is it carried in the public cloud? Or is it carried in the edge by myself, right? And I think that, one of the things that we have the opportunity to do with 5G is all these network interfaces are now defined. And what we have to figure out is the constellation of people who deliver on those services or companies that deliver on those services. What it'll still require, though, is a close cooperation and some level, higher level orchestration between the groups in order to deliver on that. Okay. The example here on the slicing for railways have a lot of real estate. A lot of times they control their own radio access. They build their own private radios for the most part. Is the cooperation such that in order to deliver to mobile broadband users who are on that rail, that I let the rail company run that slice, in essence, right? For them, the benefit is they've got control of their systems. For the users of their service, they get access to radio networks. For me as a radio supplier or mobile supplier, my users are taking advantage of that infrastructure and getting their service. All right, so there's kind of a win-win here. And I think the story's out on how these 5G networks come together. Now, when that happens, this is kind of the piece of the puzzle that has to be solved. Where's the automation across multiple domains? And how do those domains talk to each other? So, for example, in the way we've classically defined 5G, we have a level of service orchestration that tells the management systems, what needs to happen for those network functions. It works with cloud orchestration that says, I'm going to have, this network function in this particular cloud and report back to the EMS that it's up and running. All right. I also need this service orchestration, though, to communicate with my network and the WAN to orchestrate how these things connect together. So that work is where the real rubber lies, in that building the orchestration systems to support the network functions is going to be the key piece to making 5G successful here. Okay. So with that, that's where we're at. All right. So
Very good.
I
Question?
didn't tackle the Henning question. Will 5G network slicing solve all evil? I don't think so. But I think
Well, you are offering artisanal, handcrafted network slicing, aren't you?
I like that word. That was a good one from Dean.
If I'm an enterprise, why do I, using, and it doesn't matter if it's public or private 5G,
Yeah.
why do I want to go through a core network at all? Why don't I just get local breakout at the radio straight to the nearest fiber or MPLS or SD-WAN provider, the same way I do for my fixed connections?
You could. Now you're an island, though, right? So the promise I think the operators end up having is, okay, yeah, inside the island you're good, but now I don't have any other phone but my mobile, and now I have, as a user of a service provider, access to the whole world, so to speak, for my
But
my
I get that
service.
as well. So yeah, basically, what I want is have taking your railway example or the port on the first slide.
Yeah.
I want to have cell tower there, and at the base of the cell tower, I want local breakout to the nearest fiber, because the same way I run my WAN for everything else is basically this is the entry point to the WAN, and I don't want the core network gets in the way. It's fine for the carrier wants a core network because it needs to manage its own resources.
Yeah.
But if I'm using fiber and MPLS doesn't come with a core. Why do I need this thing?
Yeah, you might not. I mean, as a user, and maybe what you've decided is, I've got all my other access, and all my other resources separated up on the public cloud, and I'm going to just use CBRS and fulfill most of my needs. Anytime I'm, so to speak, in the net, in the wild, I just use my Wi-Fi connection, and I come back into my network needs. That could be very acceptable to some users. I mean, others it's not. So I'm not saying this is going to be a panacea for that. I think what it offers the opportunity is to reconstruct the networks so that it addresses what the enterprises are wanting. I think there's going to be use cases where it says, I actually do need a centralized core. I do need to connect with others, and therefore that's the role that the service provider provides, right? So, I think that there's still a lot of discussion about how do these things get realized. I mean, Nokia said very clearly they were going to go right after enterprises with radio access in the core, right? And why was that? Covering their bets, right? We're trying to, in Ericsson, we've focused a lot more on the service provider. I'm not sure where the chips are going to lie with 5G yet. I mean, I still think there's a lot of discovery that's going to occur as we go through this. And part of that discovery is, here's another case, the hospital, right? Usually they have, some level of wireless system, all their systems are connected into that. Okay, do I need the service provider network for that? Maybe not. Maybe I do, in the sense that when doctors are, on call, I need to be able to reach them, right? Maybe that's the slice that you worry about. Is just when I'm outside the walls of the hospital, to get the on call for the doctor. That's a very small slice that is carried by that. I don't know how these confederations are going to work yet. I think the promise of the 5G architecture is to actually be able to plug in different solutions, and I think one of the things that are going to come out of this is there's going to be blueprints, things that seem to work really well together. There's going to be some things that are going to be very niche. This is unique to my situation. You know? But I think the architecture has the opportunity to be able to address multiple needs. Okay.
With network slicing, is it important with interoperability between, I mean, when you have multiple operators, is there a need for then orchestration?
That's the piece that's really been undone here, right? In the 5G core, there's a lot of a lot of definition of what happens between these boxes here, right? But there really hasn't been clarity about, what happens when I go away from my network, right?
So your hospital connecting to the doctor, if the doctor is bringing
Roaming.
a device and it's on a different carrier,
Yeah.
it doesn't work.
No,
No, but then you're not going to use that doctor.
yeah. I mean, yeah. So, that the bring your own device is an interesting scenario too, right? Because now, what network am I on, right? So, yeah. I mean, it's going to tear apart some use cases and maybe reconfigure the way people are operating. That'll be a lot of, how do I take advantage of multiple networks? Yeah.
So one of the questions I had, especially in the manufacturing case, when we start to look at the edge of the network slice, we have to get out onto a radio somewhere.
Yeah.
And so we're showing shared radio, which implies that there's other traffic running on that radio network. We're going to have adequate coverage. How are we going to guarantee access to enough of that radio service to supply that business case? In other words, I know there's the concept of RAN slicing. It hasn't really been implemented.
Correct.
And a lot of this is going to reside in the scheduler, which tends to be a rather closed interface depending on,
I think this might
how do we
lend
do
back
this?
to the QoS discussion.
Yeah, it does run into the QoS.
A lot of those mechanisms are very hard to implement, especially on a shared resource like RAN, right? Yes, there's ways you can bar access, that may be it. You're dedicating that radio to purely the user. Sharing the resource and trying to bump priority, that's always going to be a challenge. Okay.
Any other questions? Very good. Thank you so much, Kelly.
Okay. Try it again. Where is it? There it is.
Let's see if we can find him. Hollingworth. There we go. Yeah, something's happening. No, that's the wrong one. Okay, there we go. All right, our next speaker, who will be the last one in this session of the track, is Jeff Hollingworth. Jeff is currently Chief Marketing Officer at Mobile Edge X and spent significant time with Ericsson previously. Jeff has also graciously agreed to join us from the infamous CQR cast of characters. So thank you very much, Jeff.
Thank you very much. Good afternoon.
I'm hoping this is going to be the most esoteric and psychedelic presentation of this whole 3 days. So my name's Jeff Hollingworth. I work for a company called Mobile EdgeX. The reason that Mobile EdgeX is different is because we don't do infrastructure, we don't do technology. We were created by the operators that are buying all of this technology. And our mission and the reason that we were created was to find who is actually going to use it so we can solve real-world problems and then bring actual business and demand back into the technology. So I'm not going to speak overly about technology. We can speak about technology if you're desperate to go down and you're missing it. But otherwise, this conversation is going to stay at the level of who is edge computing actually for. And when I say edge computing, I include in that distributed cloud, I include in that 5G, I include everything that comes next, because that's what everybody is doing. Everyone has a different symbol or a different label, but what they're really talking about is building what comes next to seize that opportunity. So we're going to run through a modeling exercise we're trying to construct on how to make a simple understanding of the landscape people are sat in, and then understand what potentially can change and what the values are. Because one thing I think Dean is bringing up underneath some of his questions is that we're not living in a greenfield world. We're living in an existing world, but people will be doing different things 5 years from now. Now, about 9 months ago, we actually released, I'm just looking, how do I put this in projector mode? I am completely Mac damaged. Which is a bit like being Windows damaged, but more expensive. Slideshow, there we go. There we go. Wow, that was awful.
The open source project.
There we go. Hey. That was, if none of us knew what latency was, that was an example of latency. And notice it had nothing to do with networking. So about 9 months ago, we released all of the research that we had inherited from Deutsche Telekom around use cases, why they needed edge, the different enablers that were required. And that's something that we called the Edge Navigator. And if you go to mobileedgex.com and click on use cases, you can see all of that research. What we are now doing is looking at the way we approach that problem and adjusting based on what we think we know now, based on our interactions. And that's what I'm going to walk you through today. And I want to start with a really taking a step back perspective. It's really hard to see the future, but we all believe we're talking about it when we're talking about it. But we tend not to be, because we're talking about an iteration of today projected tomorrow. Very hard to flip that perspective. And I think that's exactly where we are in the moment. In 2007, the biggest selling device was the Nokia 1200. It was selling 150 million devices a year. If you'd asked anybody then who was going to own the next 10, 15, 20, 100 years of mobile business, people would have said Nokia.
And obviously, the next year, Apple came out, Android came out, and they decided it wasn't about communication anymore, it was about computation. And the device was a platform where speaking was just something else that you did on it. That's where we've been for the last 10 to 12 to 13 years. When I speak to anybody today, no one tells me that Apple, Android, Amazon, they're going to live forever again, because we don't need anything else. But if we start looking through the lens of the changing experiences we start to see, then the key word that starts to come out is augmentation. Now, if you get incredibly esoteric at this point, humans are the only animals that have augmented the real world at all. And we did that through the simple adoption of language and symbols to allow ourselves to actually communicate with each other and develop constructs. And we built our own augmentation of nature. We are the only animals that understand something that's not physically there. That's why the dog that you have is a lot happier than you are. Because it always lives in the present, and when it gets food, it's happy. When it doesn't get food, it doesn't care. Whereas you're worried about whether you're going to get food, or you're worried you had too much food. But very few of us are actually living in the present. It wasn't until about the 1850s or 1700s where we started augmenting our senses. And the biggest augmentation we did at mass scale was communication, because it extended the natural augmentation of me speaking to you to me speaking to anybody anywhere, to a fixed location for most of them. Then we augmented all of our calculations around data, our applications, our processes, and that's the app revolution that's been going on. Now we're moving into a world where we're augmenting our physical reality around us from every single sense. And let's just break that down a little bit. So if you go to the App Store today on iOS, there's already over 2,000 apps that are doing something with augmented visual reality. And again, what we have to understand is, in actual fact, what we believe is real as human beings is just an interpretation of what we're receiving through all of our natural senses. All this is doing is building another level of reality that we believe is true. But it is extending what we understand in the context we are. Oral augmentation, the ability suddenly to understand in real time any language and converse in any language. One of the largest applications that's making the biggest difference to people today are ones where they're visually impaired, and there's now applications that can interpret what's being said into an audio, an oral translation. There's spatial, allowing a navigational awareness around the space even though you don't understand it, you've never been there. That's the driver of Uber, the driver of Lyft. There's a great story of someone, I think it was a Ukrainian, turning up in San Francisco who just wanted to discover the city. So they became an Uber driver in the city and was guiding everybody around. And the people that he's guiding around have just been there a day less than he has. But he is completely augmented from the point of view that he understands and he can do that full job. In London, you had to pass something called the test, meaning you had to know each street and each route, otherwise you weren't allowed to be a taxi driver. And you can still do that. It's a manual Uber. It was like before Uber. Contextual augmentation is where you can space shift. I can't be at the NBA game, but I can absolutely be at the NBA game. I can't be watching the game with my friends, but I can absolutely be watching the game with my friends. And then time shifting. I can actually move backwards and forwards through a construction site, through a historical experience. All of those things become available because, again, both of those things are just concepts. Physical resistance, I don't know if any of you have ever tried this, but there's now adaptions for hands, so you can touch virtual objects and they give resistance, so you catch them. It's pretty freaky, actually. And then the last one is what I call mechanical augmentation, meaning that there are certain machines that are becoming intelligent and human-like. So anything with the concept of autonomy or autonomous starts to take on the behaviors of something intelligent. Now, in each but one of those boxes, there are business models and values that allow people to do things they couldn't do today, that make today look very, very ineffective. And that's what I think we need to get to. Now, the next bit that we skip over, and this is tying back to some of the technical presentations, there is a reason why humans understand reality better than animals. And it's because our brains are interconnected to a much greater level than all other animals, which means that we can actually do pattern matching and we can actually make decisions and correlations that other animals cannot do. From a topology of the network, this is what we start to need to create. And this is what we don't have today. At the moment, and this is what I was hearing again from the Dean and Kelly discussion, there are very thick synapses that run through the networks today that take actually the event triggers a long distance away from the locality of what happened. And there's a whole business inside our industry called interconnection peering points that all sit at the edge of the GI interface, that then everybody resides and everybody's highly interconnected. I think as we start to move forward with edge computing and this moves further out, those interconnection points need to move further out to that points of presence, so there is a locality of understanding where that is. And this is very similar a deployment strategy I think we will see as to the starts of mobile. So anyone that's old enough in the mobile industry to remember when mobile phones started, you would buy a mobile phone because it just worked in your city, because it was valuable enough to you. And the moment you went out of the city, it just didn't have any ability to work. But in the city, it changed your life. And slowly but surely, it rolled out to that point. So the second half of this is just walking through an initiative we call Seamster, where we're trying to build an abstract model of how we understand what kinds of use cases and what kinds of edge computing can best serve those use cases. So I'm going to walk you through here the simple modeling that we have, because we are then setting up a work in progress to engage with various different companies to try and model everything consistently from a use case point of view. So the first thing that we should understand is perspective is really important. Everybody in this space is coming from their own perspective. And everybody is correct looking through the lens that they are looking through. So you have to have an open mind to understand the perspective people are speaking from and the truth that it's coming from. But there is a difference between true and truth. And one of the most surprising places that we spend a lot of time speaking about is the fact that edge computing is not a new phenomenon at all. All of us, like Kelly's using his phone today, he's using a device edge, he's using a cloud edge. The only thing is that it's passing through potentially an on-premise edge and definitely a telecom edge. But they're just providing, especially the telecom edge, connectivity. Now, each one of these edges has benefits and challenges, and each one should be used the right way. So, for example, the device edge is the most present edge for any application. Why isn't everything on a device edge? Because it becomes incredibly expensive, it becomes incredibly isolated, becomes incredibly heavy. Most of these experiences are mobile. The battery is the biggest problem. It doesn't follow, it's never followed the Moore's law. So you can start to look at offloading from those devices. Now, when we speak to, let's take an example, an Oculus Quest. Who's here has used an Oculus Quest, by the way? And do you like it? But when you put it, was it easy to set up and use? Yeah. You've just described Oculus Quest's biggest problem. So Oculus Quest is this all-in-one VR headset. And it's really good because they focused on the usability. I think you get it out of the box, you scan your room, you can play in it, it recognizes your room, it's all in one, you're not hooking it up to some PC. It's great. The problem is, still very expensive, and they're subsidizing it, by the way. I don't know if that's public knowledge, but the land grabbing on it is heavy, and thus it's not very portable. So if you can take away expense, weight, and improve battery life, they'll absolutely talk about putting in the additional cost of a modem or something like that if it increases the flexibility on it. Now, the interesting thing about Oculus Quest is the original design before that was something called Oculus Rift. And Oculus Rift actually implemented compute offload. So the games have been designed for compute offload with edge computing in mind. The only thing is, it's got a cable on the back. Number one thing people hate, cables on the back to fixed objects, so you can't move. That's more like prison than experience. Those games are perfectly architected to move to an offload that has not got a tether. Telecom edge is the most interesting because it's the least used. It's the least used by anybody other than telecom. Let's just get this. Okay, I saw Kelly gets used all the time. It's a bit like you've got the chocolate, but you're not sharing. Yeah? More investments in telecom edge over the last 10 years than all the other edges. $2 trillion. That $2 trillion is going to move into 5G, get repeated. There's no doubt about that. The only question is whether that telecom edge will be used by anybody other than telecom. So when we look at all of our network diagrams, I always look at these trying to see if anyone ever puts a user on there and how they actually connect to it. If I look at a diagram from AWS, Google, Microsoft, I don't see any technology diagrams. I see users, interfaces, and flows. But telecom edge is the reason that people are getting excited about edge computing. Because All the other edges are existing and used in some way. And the only question is how telecom edge can actually open up markets and change the status quo of today, either to improve what you're doing today or to do something that's not possible. So, for example, we believe that if we looked at how cloud rolled out, it went from public to hybrid to private. What we think Edge is going to do is go from private to hybrid to public. So we believe the first people that actually will benefit from a distributed edge are people in large enterprises with multiple on-premise edge computing constellations where the value to their business is so high, but then they need to manage and orchestrate all of those workloads across all of those locations. The moment that is not automated, the moment that is not managed, the moment that is not declarative, that is really, really hard. So just underneath users, it's actually the life cycle management of applications and operations. And of course, the centralized cloud edge is the biggest place where all developers live. We believe that edge computing applications will all be born in public cloud. And what will happen is they'll leave home as they grow up, and they'll slowly populate. The children, the parts of it that make sense, need to automatically populate edge locations when they're needed, and when they're not needed, they disappear. I was listening to a very interesting presentation yesterday from the callstats.io guy. Callstats does real-time diagnostics of WebRTC traffic to do AI, machine learning, quality assurance insights. They run probes on every single client that's passing data back. Their biggest problem is managing that data into clusters dynamically and then actually being able to gather those insights and put them back into a center of inference. That's just one app. Everybody is trying to understand with a greater granularity what's happening in real time so that it can actually make better decisions. We spoke to another person in retail who was telling us that they have deployed IoT systems out in the field, but they can't turn on all of the features because when they do, it releases this tsunami of data and it floods. They want to do that. So we have this pent-up demand, but we are not meeting it with a functional experience that's easy to use that solves those problems. So inside that landscape, we start to construct sentences and a grammar. And the three items that we see in this universe is that you have an augmented human. And the definition of an augmented human is that it's intelligent. It's more intelligent than it's not, you know. It's not saying that a non-augmented human is stupid, by the way. You have an augmented machine, which means it's intelligent. And then you have an augmented thing where it is aware. So things are objects, humans and machines are subjects, augmented humans, augmented machines. So when we document use cases, we actually went through a lot of investigation on how to inject a discipline in doing this, given the fact that there are so many different perspectives, so many different ways of viewing this world. And we actually ended up using the same approach as law students use to interpret law. And we based it on legal case briefs. So what we try and do in any scenario is we discuss first the facts. And the facts are always around an industry, a user, a value. And then we have a hypothesis on how we can adjust that for the betterment of the situation. We measure the outcome for this, and then we have a score. And the score defines how important is this use case to the people using it. Is it a 10% improvement? Is it transformative? Is it disruptive? What's the ease of adoption? How easy is it to use? And then, how is the ease of spreading? How easy is it to take it from one implementation, say in one retail shop, and do it in all retail shops? How easy is it to take it from retail to manufacturing to transportation? How portable is it? And then we try and size what's most interesting and why. And then the final part of this analysis is modeling that we use second-order thinking and third-order thinking on. So the first-order thinking of edge computing is that the proximity gives you lower latency and the ability for higher bandwidth. The second-order thinking, because you've got low latency and high bandwidth, is you can start to have compute offload, you can start to do endpoint, high-fidelity endpoint synchronization. And at the moment, that is where we are from an edge computing world. People are taking their backends and putting them on edge servers. So if I am a facial or a feature recognition company from a video analytics company, I take my backend and I put it as close as I can to the cameras and devices that are actually being served by it. It extracts the objects and it sends it out. And then if we work with another one of those companies, we take their unique backend and we put it out. And if we work with 100 of those companies, we have 100 backends all doing pretty much the same thing. What we then start to identify is the third order effect of edge, that actually feature extraction for video is actually an edge native service that should be provided for everybody rather than being maintained by 100 companies as if it's differentiated. And that's what we think needs to turn up at the edge of these networks. So some simple examples. It's quite refreshing when you start looking through this lens at how many examples are existing today and the difference they're making. And one question I think we're getting wrong as an industry is that we keep asking what's the most important use case. I think the correct answer is what's the most important use case to each of us. Because the answer to that question depends on who you are and what's important. And the power of any platform like this is to be able to accommodate the importance to everybody. But for example, there's already in utilities augmented field maintenance workers. What's the big difference? First big difference, they actually can solve and diagnose more problems because they actually get expert help when they're not expert. The second advantage is that they have less bad jobs. The quality goes up. It can say, no, you did this right, or no, you shouldn't have left the casing open. The third one is around job allocation and the ability for them to understand what the next job to do would be the best to do based on what they understand, what parts they have with them, where they are located. Example number one. Example number two is, and this is coming from the people that are building the Mars lander, so complicated assembly workers. If you've ever tried to build something complicated, having a 300-page manual by the side of you and picking it up and putting it down and putting that bolt in and going, oh crap, the Martian lander leg looks a bit off, and like carrying on like that. Two advantages. One is that they're training people before they actually do the work, so they're becoming productive twice as fast. And then it's a 68% improvement on the speed they build things. And again, less mistakes. Now, there's an example app, by the way. The consumer example of this is IKEA furniture building, where there's an app doing for that, where it will build you, it'll show you exactly in parallel on your floor as you're building the furniture. That's obviously going to be a lot bigger than the Mars lander. And then augmented healthcare worker. This is interesting because everyone always goes to this remote surgery kind of angle. There's some very simple applications that are already in service just around diagnostics. People picking up gait, whether people are not moving correctly. A lot of work around training people on recovery after accidents. The home health care, the actual discipline for taking drugs. One of the big problems after treatment is the fact that people aren't very good at maintaining their own discipline of follow-through therapy. Now, these were just 3 examples. Every single aspect of life, you can put augmented in front of it and think if it exists yet. The other one the one that really touched me was the augmented disabled people. 3.4 million people in the US that are visually impaired that this technology can change the life for. Augmented gaming, people call that Pokemon and Facebook Oculus. So what we are in the process of, and we'd love to have more conversations, is going through and finding these examples and writing them down in a very simple, consistent manner, scoring them, and then we'll start to run analysis of, well, if we involve a telecom edge, if we involve an on-prem edge, what does it really mean? Is it interesting? Is it not interesting? And that's the end.
Thank you.
Thank you.
All right, we're a couple minutes into the break time, but while we have Jeff here, is there a question or two?
So I went to Seamster, and then you go into Edge Navigator to actually take a look at these use cases. Is that how that works, Jeff?
You go to mobileedgex.com.
Okay.
And you go to the navigator. If you go to seamster.io today, you can sign up, and then we'll let you know, because we're about to open that up.
Okay.
Yeah.
Good.
Yeah. So please put your email in if you want to just go there.
So Jeff, what's the difference between a telco edge and, let's say, someone else's local data center? Let's say Edge Connects, or I don't know, Equinix put something in the nearest city.
So the way that we've tried to name these edges is almost from an ownership of type of company. So the telecom edge is the access network, either mobile or fixed, that can be used to reach one of those local data centers to transit today. And the question, so we would put the Equinix data center inside the governance of the centralized cloud edge. Because you can choose to put something in there. You don't have to ask for permission. There's no gatekeeper there. If you want to put something inside telecom, today you're getting special permission to do it, and tomorrow we're hoping we can open that up. Now, where I found your question interesting, by the way, which I thought was it was more brutal than the FCC question, I thought, was if you can do local breakout of the tower and get immediately into the local network, that's massively valuable. Because I believe as the interconnect moves out, all those tenants start to live there and you start to get the interconnection at a very localized level. So my brain analogy, I think, is quite powerful, because I think with growing synapses, the more connections we make, we won't know the topology of this thing at the end, I don't think.
All right. Jeff, thank you so much for wrapping up this session. We have a break until 3. There is a keynote next door, 3 to 4, and then we are back in here to wrap up the track at 4 o'clock. Thank you very much.
gonna talk a little bit over it, so the audio is not really important. It's just background music, anyways. Let me go to this slide. Cool. Okay, cool. I didn't realize I put so many transitions in here and everything. None. Oh, animations actually. Yeah, it's all good.
Yeah, relax. They're still next door, but your moderator or your introductory person should be coming in.
Okay. How many people are here today?
There was a good attendance yesterday. Today has been the most in this room.
Uh huh.
I would say about 12.
Okay.
Now it's thinning out.
Okay. No worries. Will the camera capture that or not really?
No, what I'm going to do is that since I have your laptop feed, I'm going to do a picture-in-picture.
Perfect.
So I'm going to have your laptop. You won't see it here. It's just on my end.
Okay.
And then I'll have a head and shoulder shot of you.
Perfect.
So I need you to stand here.
Definitely.
And talk.
It's easier because I can read some of my notes that way too.
That's fine.
Yeah.
And then he allows you to answer questions.
Okay.
So it's a half an hour.
Yeah,
So
mine's gonna be like 15, 20 minutes.
That's perfect.
Yeah.
Because then there's been more questions, a lot of questions. So you may want to give yourself time to.
Do you mind if we stop recording for the questions? Because I don't want to say anything like if they ask something about the proprietary stuff, I don't want that recorded.
That's fine.
Okay.
If you want me to stop, you can say.
Like my last slide is gonna be this one, so right after that.
I can stop. I can stop. Just say thank you, because they'll.
Exactly.
See, will they clap now or later? They may not clap until after the Q&A. Okay, when you said his name is Kevin or Kenneth, who's going to do the introduction?
I think Warren.
Oh, Warren. Okay.
Yeah. That's who I was talking to most of the time. Yeah.
Well, I'll stop it. Or when you say that concludes, this is the end.
Mhm.
I'm ready for answer. Well, however you want to phrase it, I'll stop the feed. I'll stop the recording, and you can answer your questions in the room.
Yeah, I'll probably end it with thank you for listening. If you have any questions, or I won't even say that. I'll just say thank you for listening, and then boom.
Perfect.
And then I'll be like, by the way, does anyone have any questions?
Okay,
Right, so.
that'll be my cue to stop it,
Exactly.
and then you'll have the room, and they can ask you all the questions.
Cool.
That's excellent. My name is Robert.
Sid, nice to meet you. Appreciate it. You're
Same
very
here.
helpful.
Yeah,
Yes.
I want the guests to come in early. I mean,
Yeah.
normally they're going from room to room where they're socializing,
Yeah.
networking, and then when they come in, their laptop doesn't work. They can't find their files,
Yeah.
and that chews up their time. And then they go overboard. And I'm not sure if you're going to have somebody afterwards. I need to find.
I think this is the last session, if I
Yeah.
remember correctly.
I think someone
Yeah.
will show up or
Yeah.
left.
Yeah, I think Warren said that this is the last session. So I was supposed to get here at like 10 a.m., but I was flying from New York from another conference, and there's a horrible storm going on right now. So like my flight got delayed by like 4 or 5 hours.
Oh.
Yeah, so I still made it. I literally just got here, and I'm like,
Wow.
oh, thank God, I
Well,
made it.
I'm glad you're all safe and
Yeah,
sound.
yeah, appreciate it.
Made it here in Chicago.
Yes, my old hometown.
Did you go to IIT?
No, I went to Urbana-Champaign. Yeah. Yeah. Cool. Well, I'm gonna take a restroom break real quick.
Go right in. I'll be here. We got like 10 minutes or so. goes into my power thing and then also the extension. Extension, sorry, okay, I didn't know that. Not the big one. The one that's with, okay, and then you pull back the line, network cable that goes into the screen box.
session of Programmable Telecom Networks track. A few people will join us. The keynote next door is just wrapping up. I hear the applause. So our next speaker is Sid Sharma. Sid is Director of Developer Relations and Partner Engineering at Agora.io. And Sid will be speaking on the topic of the future of the Agora real-time communications stack. So without further ado, Sid.
Great. Thank you, Chris. Hey, everybody. Hope you're having a good conference. You know, it's great to be here in you know, real-time communications conference as well.
Sorry to you that next door just broke up, so you probably need more speakers, more attendees here.
What was that?
They went a little bit over, or two over time.
Oh. Okay. Okay. Should I wait?
No, it's up to you.
I could wait. My speech is like 15 minutes. So.
Because then you back up into the other person. It's up to you.
What's that?
The other person won't be here, so.
Oh, the other person won't be here?
No.
Oh, then you might as well wait.
So I think we're waiting. Yeah, yeah. While we wait, how's the conference going for you two? Individuals in the front, yeah. Good? Okay. How's it going? Thank you. Yeah. No, not this year, because we were at NAB, so the dates conflicted. Yeah, but next year we'll be here. Yeah, I was there. I just got here from NAB. What's that? Yeah, it's great. Yeah.
So what are y'all doing that? Because that's strictly broadcasting. How would you put that in there? How are you spinning this for that audience?
For live streaming?
Yeah.
We provide the solution, so you don't have to build like the server side components and all that stuff. So
What about the encoding part of that?
the encoding and decoding is all done by us. Hey everybody, I'm Sid Sharma. I'm the Director of Developer Relations and Partner Engineering at Agora.io. Thank you guys for all joining and being at this conference. It's great to have like-minded folks in the RTC community get together and talk about the latest and greatest in this space. So really glad to be here, and I'll be chatting with you guys a little bit more at the end and trying to understand what you guys are doing as well. So I'm here today to talk about Agora.io, give you a little bit of information on what we do and what we offer to our developer base and our customer base, and then also kind of give you a sneak peek on what's coming next in our next few releases and some really cool stuff under the hood. So let's go ahead and get started. So Agora.io, for those of you who haven't heard of Agora, is the largest real-time communication API company in the world. We serve over 20 billion minutes per month, and it's growing on a daily basis, where our SDK is installed on over, now that number is 2 billion devices worldwide. So if you have some of the latest streaming apps or video communication apps, there's a good chance that you have the Agora SDK on your phone. And we've been in several different verticals: education apps, live streaming, dating, finance, you name it, and I'll show you some of the examples later on. So there's a lot of players in this space, as we all know, right? You have standard out-of-the-box WebRTC, many different API providers as well. But what's our differentiator? We don't actually use standard WebRTC except for the JavaScript SDK when you embed it into your web app. However, we use a UDP protocol that we kind of customized on our own and built a network of over 200 data centers around the world, which makes it a very, very scalable and very, very packet loss resilient network. And these 200 data centers are spread, globally. So whether you're starting in San Francisco and trying to send your data through India, China, Africa, you'll have that global latency of 200 milliseconds, because we spent 2 years in stealth mode trying to build up this network from ground up and provide the users with the best experience. So Agora provides several different flexible building blocks. From video, chat, voice chat, live streaming on both the video and audio side, messaging, recording, you name it. And then also we have a third-party extension marketplace where you can go ahead and add face filters, content moderation, transcription services, all on top of that video. So it's super easy to get started with those APIs as well, because they're a part of our partner gallery, and I'll show you a little bit more on the platform side as well later in this presentation. So let's take a look at the live streaming growth in the last couple of years. Worldwide, more and more users are trying to be on live streaming apps as broadcasters as well as audience members. Actually, if you look at the top 4 countries here on this chart, there's almost 10% for each country goes to 10% of the smartphone minutes go to live streaming viewing. So 10% of their time on a smartphone is watching someone live stream, which is crazy. And this number is growing on a daily basis. More and more people are starting to broadcast. More and more people are starting to watch. And if you look at the Agora network itself, we actually did a study, and only 3% of our RTC data that's going through our network is a standard communication use case, like one-to-one chat or group video chat. The rest are streaming, and in several different verticals: gaming, education, broadcasting, social, you name it. But 97% of our traffic is not one-to-one or group video call. So that shows how much one-to-many is growing, and interactive streaming is really taking off. And the reason why it's taking off is really because of the RTC ecosystem, right? There's several different key factors here, and I think there's 3 big ones here that I want to call out. Is the standards and protocols, right? Without AV1, without WebRTC, there's going to be a very high barrier to entry. But these type of codecs and software allow platforms like Agora and other vendors in this space to easily package this great software up and provide it as a client SDK for developers. And then on the platform side, our goal is to make RTC the simplest as possible. So any developer who's starting off can go ahead and embed this into their solution. And then obviously the app developers are a key player here, because they are the ones who are innovating, building this software into their apps and being able to build these experiences for their end users. So, and I think that relationship between the app developers and the platforms is really what drives innovation, right? The more innovative the apps become, the more the infrastructure demand grows, right? You need to continue to adapt, to scale, and then once you scale and adapt, then a new wave of apps like AR apps, VR apps come out, and you need to continuously improve on your infrastructure, and so on and so forth, and the cycle is always a continuous cycle. So now let's go into the Agora ecosystem a little bit. So as I mentioned, we have several different partners. You can go ahead and pick whichever one you want to do. But we also have several platform partners, right? We actually recently partnered with Unity, and we're one of their verified solution partners, and we're listed on their asset store. So any Unity game developer or any Unity developer in specific who wants video chat or streaming into their apps can go ahead and stay in their environment and grab it from the asset store and embed it in a few simple steps with minimal impact on their game, right? Because it's in that environment. You don't have to download excess packages. You just bring in the asset and you're good to go. Same thing if you look on the other side, on the enterprise collaboration, we actually partnered with Box.com to provide video communication inside the box. So you don't have to leave your Dropbox or your Box, your Box instance. You can go ahead and just spin up a video call, collaborate over a document right there and then. You don't have to purchase any other software for video communication in specific. And I'll show you this quick video so you guys kind of can envision what goes on. There's transcription layer, there's recording layer, there's the video communication layer, and it's very simple to add. There's no coding required, and that was kind of our biggest draw here is, coding this out or purchasing the software is not really a great experience sometimes. So this is a free software that we, put on the Box store, and anyone can go ahead and grab it and collaborate in real time. And lastly, on the platform side, we built a WordPress plugin because we really believe in the low-code, no-code story, right? We want developers to spend less time coding out the RTC portion, but really to focus on their app side, their app experience, to build unique experiences, because we don't want them to worry about building the RTC components and all that stuff. So, in WordPress, if you have a WordPress website, you can just go ahead and put a short code in after you bring the Agora plugin into your WordPress website and set up all the stuff in the background, what resolution you want, where do you want it? Do you want it on a page? Do you want it under a specific post? And you can have live streaming or video communication in a matter of seconds, actually. I think we have a video that I'll share with you guys later that it took 56 seconds to spin this up and get your first video call rolling. So now let's look at the outlook, right? You guys kind of understand what Agora is, what we do, but what's really coming next, right? So as I mentioned, a key piece of the Agora platform is our SDRTN, the software-defined real-time network. And yes, we do have 200 data centers around the world, but that's not enough, right? We want to continuously grow, build that to be more scalable, to be more network packet loss resilient, to really be able to actually provide a smooth experience no matter where the person is located, no matter what the network quality is like. So, our new next generation SDRTN actually allows you to, get up to 70-80% packet loss and still deliver a very solid user experience. So this is our current SDK stacking up amongst some of our competitors. I hid the competitor names, but if you're interested in knowing which one is which, feel free to go on YouTube and search our channel. But as you see, we're kind of bringing in inbound packet loss through the network link conditioner tool at 20, 40, 60%. And as you can see, there's some jitter, some freeze frames, but Agora is able to still withstand that and still deliver a good resolution and still be able to deliver most of the video packets that are trying to be sent. However, with this improvement on the next generation SDRTN, we can, as I mentioned, we can withstand up to 70-80%. So on the left-hand side, one of our engineers, Yuren, is on the regular SDRTM that we have in place currently today, but with the updates, it's on the right side, and you can actually go ahead and see the difference right away, and both of them are at 80% packet loss. So as you can see, the left side, he froze, it's not able to actually deliver those video frames, but on the right side, this is the new next version, and we're still able to have a smooth video quality, increasing the latency a little bit, but still being able to deliver a smooth quality of experience for the end users. One of the next updates we actually are really happy to announce is adding machine learning in the media stream, right? We've heard a lot about machine learning, AI, but we've never really seen it being done in a live video scenario. And that's exactly what we tried to do, is we tried to add AI to improve the resolution, improve the jitter for any video stream that's, say it's at 240p, it'll look like it's at 360p with this Agora super resolution. So that means less bandwidth, less packet loss, lower latency, because there's not as many video packets being delivered. And here's a quick demo of the super resolution. This is one of my hotel room keys. So as you see, the bottom button is flipping it on and off. You can see the room number, and the text is being a little fuzzy, but when it turns on, it scales up because of this AI, and it's still going in 240p. So this is actually coming very soon. We should have this out for iOS within the next month or so. And then Android is coming. It's a little bit more tricky because there's so many different hardware devices, but we're continuously working on it, and we're going to try to roll this out for all platforms very soon. And then lastly, the flexible building blocks, right? One major kind of initiative that we took is we tried to decouple the media engine and the transport layer, because at first they were all coupled together, but what if you wanted to bring your own media engine to the Agora network? You wanted to leverage our network without using our media engine. Now you have the power to do that, and this opens up doors for use cases like IoT. You don't actually have to encode and decode because it's such a small network chip that it's not possible. But this new I guess, flexible building block that we're offering of the next generation of the Agora SDK, we call it the refactored SDK, allows you to have new experiences. And one of the coolest things is there's additional benefits in the live streaming world. You can jump from one channel to another, and we call it zero-time latency. So when you have to buffer a stream, or even when you're on a live stream, you're swiping and going to the next stream, it has to load and spin up. We actually were able to do zero-time latency, and here I'll show you a demo that we did at our conference. And this is Jake. He's a developer evangelist on my team. Sometimes I'm on Musical.ly. I'm listening to Bhangra music, Indian music, and sometimes I want to listen to rap. But I can't decide sometimes, so I switch back and forth, but it takes too long to buffer, and my kind of user experience is not great. But now I can move from one stream, one channel to another, and as you can tell, they're in two different channels, channel 111 and channel 222. So it really allows you to build unique experiences for your end users with this new addition to the Agora platform. And those are some of the quick updates that we're offering. There's also more, so if you're interested, please do sign up and stay updated on what's coming. I think the future is really built by this community in the real-time communication space, right? Agora, the different players in this space, the different app developers, the different Kodak and WebRTC engineers. Everyone has a role to play here, and I think conferences like this, IIT, RTC, really help bring everyone together. And there's not many like this, but hopefully there's more coming soon. And thank you for listening. And we are also hiring. If you're interested in becoming a developer evangelist for Agora, please do let me know. Email me. And thank you so much.